Okay, no. you have a USB?
Should I test or not?
No. Not anymore because the speaker's there now.
I don't have this.
Let's see if I can put this on. Let's try to. It's not easy to transfer these. It's not working.
Why does he need to transfer this?
I mean, it's not.
Why is? But that isn't that just USB-C? You don't have a USB-C? Yes, just connect it.
Then this.
Just start it and just.
Oh, yes.
I'm sorry. So you have to connect
good.
this right to your.
Please put this on.
USB or is it USB-C?
You can just click this.
So it's a clip, yes.
And then.
Okay.
You can use that microphone.
Thank you.
You can use that
Okay.
mic if you have.
That's excellent. So.
Just a reminder, this is session F in room 4. So everyone who's in the wrong room, in the wrong session, you can still leave to the other room. All right. So the first speaker of this afternoon session is Takeda, and the stage is yours. You have 50 minutes and 5 minutes to the end. I'll show you 5, right? 10 minutes. But that includes your question.
Including question 50 minutes.
After 10 minutes, you have 50 minutes, but this includes your question.
Okay. So let's start. Hello. So can you hear me? Okay. So I'm Takeda from Kyoto University. So thank you for organizing this wonderful conference and giving me the opportunity to speak today. Today I would like to present my recent work on quantum decoherence of gravitational waves based on this paper. So first I will give a brief introduction. The unification of gravity and quantum theory remains one of the major goals in physics. This figure illustrates the relationship between different fundamental theories. Quantum field theory combines special relativity and quantum mechanics, successfully describing the 3 of the 4 fundamental interactions in the standard model. However, gravity is not part of this framework. To advance quantum gravity, it is crucial to experimentally test the general relativity and the extreme conditions and search for the possible quantum effects in the gravitational interaction. However, even at the low energy scales, such in the laboratory scale, so there is no experimental evidence that gravitational degrees of freedom are quantized. So the key question of my talk is that can we provide experimental evidence that gravity is quantized? So by applying the recent quantum sensing techniques, so several experimental proposals aim to verify the quantum nature of gravity. So there are 2 main different approaches. The first proposed by both Murray-Bedlar, so involves preparing the massive object in spatial superpositions and tests whether gravity can induce entanglement. So the many variants have been proposed and their implications are still debated. But yeah, in particular, even if the gravitational induced entanglement is observed, it would not directly confirm the quantization of gravity because the classical Newton gravity can induce the quantum entanglement between the such quantum matter systems. The second approach is more direct, so it seeks to detect the hypothetical quantum carriers, so-called gravitons. So since the Dyson's early discussion, so the possibility of graviton detection has been debated. So the recent work suggested that quantum sensing might make such detection feasible, but yet the tasks remains extremely hard, challenging. So as an alternative, sorry, how to use this? Yeah. As an alternative, several works explore the indirect detection, in which specifically it's searching for the gravitational decoherence of the matter caused by the environment of gravitons. So in recent years, detectability of particle or quantum nature of gravitational waves has been actively discussed. So this is important for probing not only for the probing the quantum nature of gravity, but also potentially the understanding of the early universe. So to clearly distinguish quantum behavior from classical behavior of gravitational waves, they must exist in non-trivial quantum states, such as squeezed state. So by analogy with quantum optics. So such non-trivial states are naturally predicted by standard inferential models and may help distinguish primordial gravitational waves from astrophysical ones. So however, these quantum coherence may be lost due to interactions with the cosmic environment, so during gravitational waves propagation, so leading to decoherence. So therefore, we evaluate the quantum decoherence of gravitational waves to address the question, can the gravitons retain their quantum nature? So we consider a simple environmental model where a massive scalar field is conformally coupled to gravity. So by perturbing the metric and scalar field and an expanded universe, we obtain a perturbed action up to the third order in perturbations. We treat H, representing gravitational waves, as a system variable, and chi, redefined scalar field, chi as environmental variable, which we will trace out later. So this scalar field serves as a proxy for the cosmic environmental matters, such as photons, neutrinos, or the other fields, other matter fields. So in the closed time path formalism, so also known as Keldt-Schwinger or informalism, the reduced density matrix can be expressed in terms of the influence functional, as shown in this expression. And if the total density matrix is initially uncorrelated. So the quantities labeled by plus minus corresponds to the different passes in the closed time path integral. And this eta represents the conformal time. So we expand the influence action up to the second order in the couplings and the Planck constant to obtain this expression. So here the noise and the dissipation kernels N and D are given by these expressions. So as we will see later, this term, this surrounded by orange, gives the coherence function of the gravitational waves. So our primary task reduced to evaluating the noise kernel, which is associated with one loop bubble diagram. So in the short wavelength limit and the quasi constant approximation, we adapt the Feynman propagators, which includes both vacuum part and thermal part. So yeah, and I will skip the details because they are detailed calculations because they are quite lengthy. But as a result, we obtain this expression for the noise kernel. So red part corresponds to the thermal part, while the term marked in blue gives a vacuum contribution. The noise kernel is divided into three regions, reflecting the condition that internal momentum can contribute the loop integral. So the dominant contribution is dominant contribution is highlighted by orange line. So since the effective action is quadratic, we can perform the path integral by substituting the classical solutions. So to obtain this expression, here the gamma is the decoherence function, which is defined by this expression using the noise kernel, so which governs the quantum decoherence of the gravitational waves. So now, by explicitly specifying the classical solution, we evaluate the decoherence of the primordial gravitational waves generated during inflation. Since the dominant contribution is expected from the radiation dominated error, so we approximate the classical solutions using the mode functions in the error. We also assume that the gravitational waves are observed in a finite region of space-time and model them as Gaussian wave packets for simplicity. We set our parameters as follows. Please take a but the initial time is taken to be the reheating time, and the scale factor is normalized at that moment. We evaluate the mass and temperature and gravitational wave momentum and its variance at the reheating time because the dominant contribution arises from an early stage in the radiation-dominated area. So we set the effective mass as massless, since at that time, the most of the particles are relativistic. And the initial amplitude is determined by assuming instantaneous reheating after inflation. Since the detectable gravitational wave signal should include at least a few oscillations, we set the variance equal to the momentum itself, which gives the minimum value or the conservative value for decoherence. Performing the integration, we find the quantum decoherence function for the gravitational waves. The function f, this f is a function obtained by integrating the mode over time. So it behaves like a step function with respect to the energy, so taking a non-zero value below the gravitational wave momentum, and determining how different energy components contribute to decoherence. The noise kernel is made by this expression, and having the strong temperature dependence determines how strongly each energy component contributes to decoherence. So using this result, we can find the amplitude threshold below which quantum decoherence is negligible. The order of the decoherence function can be estimated by this expression. And so this figure shows the amplitude fundamental decoherence limit as a function of the reheating time and the observed gravitational wave frequency. We find for higher reheating temperatures and lower gravitational frequencies, the quantum decoherence is stronger. So next, we consider the cosmic history before the radiation-dominated era. Here we assume that the matter-dominant phase follows inflation, precedes the radiation-dominated era. So by accounting for the amplitude evolution in the matter-dominant phase, we can plot the decoherence function as a function of the reheating temperature and the observed gravitational wave frequency. And this black line corresponds to the gravitational wave that horizon out at the end of inflation. So in this case, we can estimate the decoherence function by these expressions. So we needed to focus on the region below the black line and above this line, because the decoherence can be negligible when the decoherence function is less than unity. So we conclude that the gravitational waves generated by inflation can retain their quantum nature only in a limited parameter region. So this is summary. So we investigated whether gravitational waves retain their quantum nature. So using the environmental model where scalar field is conformally coupled with gravity, we found that quantum decoherence of gravitational waves is stronger at lower frequencies and higher reheating temperatures. We identified a model-independent amplitude threshold, so which decoherence is negligible, providing a fundamental limit for directly probing the quantum nature of gravity and the inflation mechanism. In the standard cosmological scenario, decoherence can be avoided within the frequency window in the range from the 100 Hz to the 10 to 8 Hz, which depends on the energy density or the reheating temperatures. That's it. Thank you for attention.
Yeah, thank you very much. So is there any question for the speaker? Anyone who wants to ask? So then you use that one. Exactly. You want to? You can go there. Where is it? Yeah. Okay.
Thank you. Thank you. Nice talk. So I think it's clear from your summary, but so you said that you did the calculation in the end for the matter field, conformal coupling and massless in the end, right? So that you exploit the conformal symmetry and relate the calculation in Robertson-Walker to a flat space calculation. Is that correct?
So Are you asking why we choose the conformal couplings?
Well, first I was confirming that you had done the calculation for conformal coupling and massless fields. Is that correct?
Yes, yes.
And the reason why you were doing that, I guess, is to relate the calculation in Robertson-Walker to one in flat space, right?
Right. Yeah.
Okay.
Yes.
Okay.
Actually, when we focus on the massless case, we can consider the case with the minimal coupling. But in this case, we want to use the usual Feynman propagators. In that case, we need to focus on the conformal couplings. In this case, we can calculate it. So yeah, that's the reason why.
Okay. Thank you.
That's the.
Okay.
Yes, exactly. You have to connect that to. Maybe you can attach that to this band
Okay.
here screen.
This.
You can either use this microphone or the other.
I think. Is it working?
Yes, no, it's good.
Okay.
But you have to use that one. This is just for the online audience.
Ah, okay, okay.
So maybe we need that here for that.
So started. Okay. It's
After
working.
10 minutes, I show you 5, which means that there's still 5 minutes left, but that includes your questions.
Okay. Thank you.
So our next speaker is Kaku. Please, the stage is yours.
Okay, thank you for introduction. I'm Kaku from Kobe University, and today I would like to give talk on sudden decoherence by resonant particle excitation for testing graphene-induced entanglement. And this work is collaborated with Tomohiro Fushita and Akira Matsumura, and this work is based on this RQI paper. Okay, so first let me start from the introduction. And as we know, we still don't know much things about quantum gravity theory, and we need experimental evidence to explore quantum gravity. So here I draw a schematic picture where each axis shows Planck constant, 1 over light velocity, and gravitational constant. And if we say quantum gravity theory, we imagine a theory which works in this region, where all of these constants are non-negligible. However, since this scale is quantum scale, relativistic, and strong gravity region, it is hard to do the experiment in such high energy scale. So for now, many people are considering to do experiment in this red region, which corresponds to the non-relativistic region. And if we do some experiment in this non-relativistic region, we won't be able to seek into the quantum gravity theory, but instead we will be able to know something about the non-relativistic gravity combined with the quantum mechanics. Okay, so in today's talk, I also would like to consider how to test the quantum nature of non-relativistic gravity. And before I move on to our main work, I'd like to introduce the original work done by Bose et al. And Marotte and Federal in 2017, which is referred to as BMB proposals. Okay, so the main idea of the BMB proposal is to answer this question. So can Newtonian gravity generate quantum entanglement? And here I propose 2 examples of the gravity model and see if they can create entanglement or not. So for example, let us first focus on the first quantized Newtonian gravity. So here I wrote 2 systems which can be explained quantum mechanically. So one is the mass source system, which is in a quantum superposition of the different positions left and right. And also I consider the probe-particle system, which feels gravity induced by this mass source system. And here, if we suppose that the Newtonian gravity is given by this form, which is the first quantized version of the usual classical Newtonian gravity, you can see that this probe-particle system feels different gravity depending on this mass source position, left or right, and it eventually evolves like this. Okay, and also you can see from this interaction that the operator of these 2 systems couple via this QG interaction. So in this model, you can see the gravity-induced entanglement. Okay, and on the other hand, if we consider the semi-classical gravity case, the things will be a little bit different. So again, we consider 2 systems which can be explained quantum mechanically. and the mass source is in a superposition, and the probe system feels gravity from this mass source system. And here, we suppose that the Newtonian gravity is given by this semi-classical form. So the difference between these QG cases is that we take expectation value over the mass source system, so that this Newtonian potential does not depend on the position operator, y hat, but instead it only depends on its expectation value. Okay, and in this case, since the Newtonian potential does not depend on a specific position of this mass source system, left or right, the probe systems only feels the one classical configuration of the gravity and evolves along a one classical trajectory. And in such case, you can see that there's no coupling between these two, there's no operator coupling between these two systems, so eventually there's no entanglement in this gravity model. Okay, so this is the main idea of the BB proposals. And if we could realize this BB proposal and verify if gravity can create quantum entanglement or not, then we can rule out either of these gravity models. Okay, however, if we really want to realize these BB proposals, there's a practical issue. That is, gravity is too weak to generate enough entanglement. So in today's talk, I want to look for an observable that is sensitive to the difference between this QG model and CC model. And we're going to see that the sudden decoherence is useful to see these differences. Okay. So now I would like to move on to the main part, the sudden decoherence by resonant particle excitation for testing gravity-induced entanglement. Okay. So first of all, let me explain our setup. So here we're going to consider the combined system of the qubit, control qubit, and oscillator system, like here. And we also consider a particle system. And suppose that these two systems are interacting via a QG. So later on, I will also going to describe briefly about the semi-classical gravity case, but here I only focus on the QG interaction. And also, I suppose that this oscillator frequency is controlled by this qubit state. So for example, when the qubit state is in state 0, then the oscillator oscillates with frequency omega 0. And if the qubit state is in state 1, then this oscillator oscillates with frequency omega 1. And this looks like toy model, but actually we can realize this kind of setup using the optomechanical system. But since there's a time limitation, I will skip the details here. And also, we suppose that this particle system is trapped in a shallow potential, described by this postulator potential. Okay, so that's the setup, and here's the Hamiltonian for this system. So we consider the Hamiltonian for the particle system, Hamiltonian for the qubit oscillator system, and gravitational interaction between these two systems. So first, the Hamiltonian for the particle system is given by this form, where the trapping potential is now supposed to be this postulator potential. And I only briefly explained the eigen system of this postulator potential. So in this postulator, so first of all, the postulator potential looks like this shape. So there's a flat potential and there's a small dip in the middle. And in this case, we first have the ground state here. So there's only a single ground state which is bounded inside this small dip. And also, if we put the energy larger than this h over h bar omega bar, then you will also obtain the unbound excited states. And this excited states has a continuum spectrum in this system. Okay, and also here's the Hamiltonian for the qubit oscillator system, which is given by this form. And this looks like the usual harmonic oscillator potential, but the difference is that the frequency, omega, is now controlled by the qubit system, 0 and 1. And here's the important thing. So we are going to suppose that this omega 0, omega 1 sustains the inequality like this. So where this omega b is the frequency corresponding to the, I think it's like, you cannot see here, but so omega b corresponds to the depth of this small dip here. Okay, so that means if oscillator is oscillating with frequency omega 1, then this particle earns enough energy to pops out of the potential dip and, via this QG interaction. And vice versa, if oscillator is oscillating with frequency omega 0, then the particle does not earn enough energy, so it still stays inside the small dip. Okay, so that's some tuning in our setup. And finally, we consider the QC interaction between oscillator and particle system, which is given by this form. So it's the usual first quantized medium potential. And then we suppose that the distance between these two systems is large enough and impose this some approximation. So here, this small g is the non-dimensional gravitational coupling. And you can also see the operator couples here, the operator for the particle and the oscillator system couples here, which leads to the gravity-induced entanglement, as we see in the BMP proposals. Okay, now let's consider time evolution in this system. So first of all, we suppose that the initial state is given by this form. So the particle state and the qubit oscillator system is initially given by a separable state like this, where the particle is initially in a bound state inside the dip, and the qubit oscillator system is given by a superposition of the coherent states with a different frequency, omega 0 and omega 1. Okay. And then if we act the time evolution operator with Hamiltonian I explained in the previous slide, then we also obtain a time evolved state like this one. So it's roughly given by the initial state plus some deviation due to the gravity. Okay, now if you look at here, you can see that this is the particle state, which is given by the combination of the excited states. And here you can see that the qubit oscillator system is oscillating with frequency omega 1. So that means you will see the gravitational excitation of the particle occurs only when the oscillator is oscillating with frequency omega 1. Okay, and also you can see that the particle is now evolving differently depending on the frequency of the oscillator system. You can see that there's a gravity-induced entanglement between the oscillator system and the particle system. Okay, so now let's consider to do the interference experiment for this setup. So here I'm going to show the interference visibility of the qubit oscillator system. So the interference visibility is defined as here. So we take the inner product with the qubit state 1 and 0 like this, and then trace out the rest of the systems. And after we do some calculation, we obtain this kind of form as the visibility. So you can see this is given by the periodic function. And if we plot this one, you get this kind of plot. So you can see that as the observation time t grows, the visibility once decoheres and then recoheres again, and it oscillates periodically. So this is, you can see this kind of decoherence and recoherence it's a typical behavior in the combined systems interference fringe. Okay, so now finally I'm going to introduce the sound decoherence. This is the main part of our work. So here I want to show that the interference visibility changes drastically when we observe the particle excitation. So here's what we're going to do. So first of all, let's suppose that we observe the particle excitation of this guy. And if we observe the particle excitation, the state collapses into this form. So after we act the projection operator, then we are left with the gravitational excitation term like this. And we get this state collapse with the probability given here. So you see that the particle excitation occurs with a very low probability, which is proportional to the gravitational coupling G squared. Okay, then after we observe the particle excitation, the visibility reaches to this form. So you can see that since we are now left with the qubit state 1, and if we take the inner product with this state 0 here, we get 0 as the visibility. So now you can see that the sudden decoherence occurs with this low frequency P excitation. Okay. So now I would like to move on to the discussion and the conclusion. So before I summarize my talk, I also would like to introduce what happens if we consider the semi-classical gravity case. So the potential for the semi-classical gravity case is given by this form. So where we take expectation value over the one of the systems. And if we follow the similar calculation, the timeable state under the single constant gravity is given by this one. So this looks like similar, like we have the initial state plus deviation due to the gravity. And we also have the excitation of the particle here. But the difference is that there's the qubit oscillator system is given by omega-0 coherent state and also omega-1 coherent state. So that means the particle excitation is equally occurred for this frequency omega-0 and omega-1. And eventually, the interference visibility after observing this particle excitation leads to this one. So you can see that there's no sonotic coherence, and we still have the periodic function here. So you can see that the sonotic coherence is exclusively happens in the QC case. Okay, so here's the conclusion. So the important thing is that here, so in the QG case, there's a gravity-induced entanglement, and we also see the sonotic coherence. But in the CZ case, there's no entanglement, and we don't see the sonotic coherence here. Okay, thank you very much.
So did you do an estimate of some typical parameter values where what's the time that it would take depending on the masses? Could you give us a feeling of how feasible this would be to implement experimentally?
You mean, what is the feasibility of this experiment, you mean?
What kind of, an example of parameters?
Yes, we did. So I didn't explain the details here, but so in our paper, we studied the example of the optomechanical system setup. And in that case, so we will see the sound coherence phenomena with a very low probability, and that probability is estimated to be very, very small, like, for a second, like this. So I think you can see the parameters here, but so this is the probability to observe the particle excitation in a one experiment. So we can see this is like super small. So what we have to do is like you have to continue this kind of experiment several times until you see the particle excitation. And once you see the particle excitation, you will obtain a sonotic coherence, which is very different in two different gravity models.
Okay, thank you.
Thank you very much.
That means you have 5 minutes. That includes the questions, right?
15 minutes including questions.
Including questions.
Okay, so I'm Eiri Wakakuwa from Nagara University, Japan. And today I would like to talk about how to detect, or how is it possible to detect the post-Newtonian classical and quantum gravitational effect in quantum clock interferometry. So after a century, we still do not know much about the intersection between general relativity and quantum mechanics. Recently, several low-energy experiments have been proposed to probe this intersection, which is often called the tabletop experiment. For example, a quantum probe of general relativistic proper time in interferometric setup has been proposed in 2011. And the scheme to witness the quantumness of gravity via gravity-mediated entanglement is proposed in 2017. But most of the previous researches along this line deals only with Newtonian gravity, with only a few exceptions. This is not surprising because the original motivation of these researches is to detect gravitational and quantum effect in low-energy regime that is accessible in laboratory experiments. But it is also true that if we are restricted in the Newtonian regime, it is not possible to detect the dynamical aspects of gravity. Also, even if we obtain some signature of quantumness of gravity, we cannot conclude that spacetime is quantum. So in this talk, we'd like to ask the detectability of this intersection in a regime where lower order post-Newtonian effect is relevant, but still in relatively low energy scale compared to the Planck scale physics. So this is the outline of my research. We consider a gravito-magnetic clock effect, which is a genuinely post-Newtonian effect in the context of quantum clock interferometry. First, we consider interferometric visibility setup to test this effect, and then convert this scheme to the test of gravity-mediated entanglement. We also consider quantum equivalence principle in this context and investigate its implication to the GME experiment. So what is gravito-magnetic clock effect? It is known that space-time around a rotating mass is dragged, which is called the frame dragging effect. This is a genuinely post-Newtonian effect caused by the non-zero G0I components of the space-time metric. And one of the phenomena caused by the frame dragging effect is gravito-magnetic clock effect. Suppose that there is a source mass which is rotating along a fixed axis, and the clock passes nearby. And the proper time that the clock ticks is shorter in the co-rotating orbit and longer in the counter-rotating orbit. This is gravito-magnetic clock effect. The space-time metric at the point distant from the source is approximately given by this form. Here, the first three terms corresponds to, let's say, the Schwarzschild component of the metric, which includes all Newtonian contribution to the gravitational field, and the last term corresponds to the frame dragging effect. So we consider interferometric visibility experiment to detect the gravito-magnetic clock effect. This is an extension of an experiment proposed for homogeneous gravitational field in 2011. So we consider the set of Mach-Zehnder type interferometry of quantum clock particles. And at the center of the interferometry, there is a source mass that is rotating in a fixed direction. The idea is to observe the interference pattern as a function of the width of the interferometer. Because of the gravito-magnetic clock effect, the proper time on the left pass is longer than proper time on the right pass. So after levitating near the source, the clock state becomes different depending on the left pass and right pass. This means that the which pass information is encoded in the clock degree of freedom, and this leads to the modulation of visibility. The important thing is that the Newtonian contributions to the proper time cancel on each pass because of the symmetry. So any observed effect is post-Newtonian effect. Then how the interference pattern look like? For simplicity, we assume that the clock degree of freedom is represented as a two-level system with a rest Hamiltonian H-hat rest. And the initial state is an equal superposition of the ground state and the excited state. The evolution of the internal state is represented by the rest Hamiltonian and the proper time. In particular, it is convenient to consider the relative evolution operator, which is UR, and this is given by the rest Hamiltonian and the proper time difference. And again, the important thing is that this proper time difference is genuinely a post-Newtonian effect. The detection probabilities are calculated as follows, and is shown in this graph. The first cosine term here represents the amplitude modulation, and the second term corresponds to the phase shift. So if delta E is equal to 0, then there is no clock degree of freedom and no amplitude modulation. Whereas if delta is not equal to 0, then there is an amplitude modulation. Now we convert this scheme to the GME experiment. The setup is almost the same as before, except that the source mass is in a superposition of the opposite rotational directions. Because the proper times on the path depend on the rotational directions, this setup leads to generation of entanglement between the source mass and clock particle. And to ensure that the entanglement is established between the source mass and the clock particle, we adopt the field disentanglement scheme proposed by Higgins in 2024. To analyze this scheme, we make some assumptions. The first one is the assumption of superposition of classical gravitational field. This means that the state of the gravitational field is represented as a superposition of classical configuration of gravitational field, and each of the configurations is described by general relativity. And another assumption is that the back action of the clock particle to the gravitational field is negligibly small. In the circuit model, the situation is represented like this. We have 3 qubits, the rotational degree of freedom of the source, and the path and clock degrees of freedom of the clock particle. The interaction is described as a controlled phase gate. The entanglement between S and PC is simply given by the channel entropy of the detection probability in the interferometric visibility experiment. And the entanglement between S and P is calculated in this way and shown in this graph. Again, if delta E is zero, there is no amplitude modulation. And if delta is not equal to 0, then there is an amplitude modulation. Now we consider quantum equivalence principle in this context. Actually, it is QEP in non-static spacetime. And this is an extension of QEP in static spacetime proposed in 2018. The time evolution of the clock particle is represented by Gaussian. In Gaussian, the internal degree of freedom is described by Hamiltonian, and the external degree of freedom is described by Lagrangian. And this Gaussian is simply given by the product of the rest Hamiltonian and the derivative of proper time with respect to the coordinate time. And in the low energy approximation, this derivative can be expanded like this. The first term is corresponding to the time, special relativist time dilation. The second term, the gravitational redshift, and the last term corresponds to the frame-dragging effect. As a test theory for the violation of QEP, we consider a Gaussian in this form. So we assign 2 different Hamiltonians for the first 3 terms and the last term. So we assume that in the Newtonian limit QEP holds. So let's say we assign, the Newtonian Hamiltonian for the first 3 terms and the frame-dragging Hamiltonian for the last term. Then the QEP in non-static spacetime is represented as the equality between Newtonian Hamiltonian and frame-dragging Hamiltonian. And in particular, this means that the 2 Hamiltonians commute. The important thing is that QEP endures the geometric picture of gravity. So if any violation of QEP is observed, then we must abandon the geometric picture of gravitational gravity. So how the QEP violation is observed in clock interferometry? For simplicity, we consider 2 Hamiltonians that have the same spectra. We assume that the initial state is in the ground state of the Newtonian Hamiltonian, which is in general expanded by the eigenvector of the frame-dragging Hamiltonian like this. And again, it is convenient to consider the relative evolution operator, which is described by approximately given by the frame-dragging Hamiltonian and the proper time difference. If the 2 Hamiltonians does not commute, then the expectation value of this relative evolution operator, its absolute value is strictly smaller than 1, which leads to the modulation of interferometric amplitude. And that modulation is observed both in interferometric visibility experiment and GME experiment like this. In particular, if the amplitude modulation is observed in GME experiment, this means that gravity is, yes, quantum, but it cannot be interpreted as the quantumness of space-time geometry. So finally, let me ask the feasibility. The typical transition frequency of quantum clock is about 10 to 15, and the typical rest mass energy of quantum clock is about 10 to 26. For the width of the interferometer, let's say 1 millimeter, and if the angular momentum of the source is J, then the amplitude modulation and phase shift is given by J to J times 10 to the power 26, 10 minus 26, and J times 10 to the power minus 15. So the effect is actually too small in any realistic parameter regions. So the proposed scheme is unfortunately no more than redundant experiment. But it is still interesting to think what does this feasibility mean. So we can consider 3 possibilities. The first one is that our scheme is just not good. In this case, an alternative experimental scheme would be necessary to detect the post-Newtonian gravitational effect in low energy regime. The second possibility is that the quantum nature of post-Newtonian gravity cannot be detected at low energy, even if Newtonian gravity can be. In this case, this means that the high energy experiment is necessary to detect post-Newtonian quantum gravitational effect. And the third possibility, which I think is most interesting, is that post-Newtonian gravity is classical, even if Newtonian gravity is quantum. This means that quantumness of gravity is regime dependent. So in summary, we have proposed an experimental scheme to detect post-Newtonian gravitational effect in quantum clock interferometry. We apply this framework to interferometry visibility experiment, GMA experiment, and quantum equivalence principle. And the effects are too small to be detected in realistic scenario. And we have discussed possible interpretations of this feasibility. Thank you.
Yes, so can you hear me?
We changed the battery.
Okay.
Please sign that this particular if you get funding from the cost section, you won't get any funding from staying in the don't sign. Is there anyone with a pen?
Sorry. To think about what you're going to ask.
Yeah. Can you hear me now clearly? Okay. So I was wondering, your Hamiltonians were derived by multiplying the Hamiltonian in the West frame with a redshift factor. And I was wondering, couldn't you use the redshift factor itself?
Sorry, I can't hear you clearly.
Is it better like this? Closer, like this?
It's fine.
It's okay. Can you? No, it's fine. So I was wondering, couldn't you use a superposition of different gravitational redshift factors to detect non-Newtonian quantum features? Like the frame tracking seems to be only one contribution to the gravitational redshift. So couldn't you get a stronger effect by considering the full redshift?
What do you mean by permutation?
So I mean, when you do this derivative of coordinate time and proper time.
Yeah, proper time, okay.
Yeah. unless I'm very mistaken now, I think that's the redshift factor. So the point is, couldn't you use just a superposition of different redshifts? Like, wouldn't that give a stronger effect, or am I missing something?
I'm sorry, I can't hear you clearly. So let's talk later. Yeah. Sorry.
Yes.
It was clear.
Okay, so I'll try to talk for.
Wait a second, where's the microphone? Do you still have a microphone?
Oh, sorry.
Thanks. You have to attach that somehow. Let's put it there.
Thank you. You're welcome. Okay, thank you very much for this opportunity to talk here. So I'll switch gears and talk about actual experiments that we're trying to do in the lab. So we're trying to push this. So we heard a great deal about a very good overview in the morning from both Richard and Dan here. So we're trying to experimentally push this direction as far as we can, and we would like to see if we can generate entanglement with utilizing gravity. And we're trying to do this in my group using milligram scale pendulums. So I'm located at IST Austria in the outskirts of Vienna, and in my group we have a few experimental directions. We do experiments with cold atoms in cavities, we do milligram scale optomechanics, and we also do some hybrid atom optomechanical systems to see if we can control mechanical systems better utilizing cold atoms. But today I'm going to focus on this here. Okay, so as I said, we heard a good overview, but let me give you my version in 3 lines here. So we're trying to catch a glimpse of quantum mechanical nature of gravitational fields in a sense. A few equivalent formulations of this question, if you ask me, is can gravitational fields exist in quantum superposition states? Can 2 masses become entangled through their gravitational interactions? Or more generally, can gravitational fields transfer quantum information? And I'm posing it in many different ways like this because over the years there have been many different proposals, starting from entanglement-based proposals relying on LOCC arguments, as we heard, to no entanglement proposals where you try to transfer quantum information without entanglement, or more recently, just looking at the diffusion in the motion of mechanical systems that are induced by just the mere gravitational interactions of objects. So with any of these methods, you might be able to say something about the gravitational, quantum mechanical nature of gravitational fields. So let me dive into the state of the art as far as experiments go. Okay, so on the left we have the largest object in the world in the quantum-dominated regime. It's of order 10 milligrams. It's an acoustic bulk wave resonator oscillating at 10 gigahertz. And they're being able to put this system in Schrödinger cat states. But from a realistic point of view, a 10 gigahertz oscillator in a solid state system is not going to be able to do, likely, gravitationally interesting stuff. So from the gravitational side, we have the smallest object whose gravitational interaction has been detected is this 90 milligram gold ball spheres a few years back. But the more relevant question is, what is the status at the interface? So, and I'm going to show you in a few slides a plot where we actually have a figure of merit and where we can put in numbers, how everybody's doing in this. So the name of the game is, we want to bring quantum mechanics to higher masses, we want to bring gravity to lower masses, okay? Okay, so in my group, the vision is the following. We build milligram scale torsional pendulums that are of order millimeter scale in size. We try to interface them with optical cavities, one, to measure their motion very well, two, to make their motion quantum noise dominated through a radiation pressure interaction. And eventually the long-term goal is to observe gravitational mediated entanglement. An idea would be to have these torsion pendulums, 2 copies of them, both coupled to their respective cavities, and interacting with each other through the gravitational interaction between pendulums, and then you ask, can I see quantum correlations between the light that's coming out of the respective cavities that are mediated by the gravitational interactions of these pendulums. So this is inspired by some of these proposals that are out there. Okay, so so I'm going to tell you about our pendulums and some potential gravity measurements. So this is what a typical experiment of ours looks like. So this is a tiny vacuum chamber. It's like this big. This is a 5-meter suspension fiber that's etched down to 10 microns, and this 10 is not a special number. We can go down to a few microns. And then we take a piece of a tiny mirror and then glue the suspension fibers onto the pendulums. And using an optical lever, we can measure the angular motion of this torsion pendulum. Or by sending light, for example, to the side of the pendulum, we can apply radiation pressure forces to act on the motion of this pendulum. And what we have done with this system is by doing measurement and radiation pressure-based feedback control, we have taken this system from room temperature, where it has 10 to the 12 excitation quanta in torsional motion. We have taken it down to 240 microkelvins, where it is critically damped. So where at this temperature, it turns out we were not aware of this when we were doing it, but it turns out that this temperature is 30 times below anyone has achieved in the mass range from 1 microgram to 10 kilograms. So this kind of gives us the idea that, okay, we're perhaps dealing with the correct mass regime and we can push this direction further, but we're still at 10 to the 5 excitation quanta at this temperature. So we would like to bring this down in principle to 1 or 0. So we know how to get to 1,000. It's just simply by improving the suspension quality. And then the question is, how do we get there from there to ground state? But let me step back for a second. All great, we're cooling pendulums, but what does this mean for the interface of quantum mechanics and gravity? And I would like to focus on this concept of quantum coherence length for matter waves. And we're utilizing this number for being able to put all of the experiments out there into a chart where we can make a claim who is doing how well or not, if we're doing well or not at the interface of quantum mechanics and gravity. So, okay, so what is coherence length? It's technically speaking the length scale where if you're trying to do any kind of an interference experiment, it's a length scale where you would lose, the interference fringes of the object will wash out. So, and in practice, any kind of a physical system has an associated quantum coherence length with it, since everything, perhaps except gravity, is quantum. Okay, so for a thermal state of a harmonic oscillator, for example, if you were in the ground state, the coherence length is the 0-point fluctuations length. But if you're in a thermal state with an excitation number of n, you just divide that length by square root of n, you get the coherence length. And the total uncertainty in the position, incidentally, turns out to be the 0-point fluctuations times the square root of the number of excitations, and nicely the product is conserved, where the coherence length times the uncertainty in position is a conserved quantity. So these kind of analyses date back all the way to 2001 and perhaps earlier. But for our system, what is the coherence length? If we put in the numbers, given our temperatures and the physical properties of our system, you get a quantum coherence length of 10 to the minus 18 meters. That's 1,000th of an atomic nucleus. So you might think that this number is very small, especially when you think about proposals where they're trying to separate the wave packets by 100 microns and trying to put them next to each other to do interferometers. But if you put together the amount of gravitational force gradient you can get from these massive systems, the coherence length and the coherence durations, here's what you get. So I have a backup slide about this figure of merit that we're utilizing. Essentially, in the figure of merit, we have the coherence length,
we have the inter-object force gradient and the mechanical losses or the damping time of the system. So you can form a dimensionless quantity from these other quantities such that if this eta becomes larger than 1, there is a scheme to measure entanglement in your system. Okay, so in this plot there's a lot of information. So x-axis is the mass of many experiments that had been carried out to date. Starts from nanospheres, goes to ton scale gravitational bar detectors. We see a few things. Data points are the figure of merit extracted from experiments, and the bars associated with each of these experiments is what would have happened if they managed to cool down to ground state. So what we see is in the low mass regime, there are a lot of systems that are cooled down to their ground state, but they're not necessarily, they don't possess a high figure of merit for doing experiments at the interface of the quantum mechanics and gravity. On the high mass inside, we see that this point is LIGO. So LIGO has cooled their mirrors down to, by feedback cooling, down to n equals 10 excitation number. And that's by a couple of orders of magnitude. The figure of merit for their experiment is the highest. This assumes if you take 2 of their pendulums, put them right next to each other, and try to do a protocol. But what you see is it doesn't have much of a potential to push further since that experiment is not designed for that. And finally comes our experiment where right behind LIGO, but above everything else, that we have a figure of merit nearing 10 to the minus 5. And this is again telling us that perhaps this milligram scale region is the correct region to push, because instead of dealing with megawatts of lights inside of optical cavities, we can do this experiment with microwatts or maximum milliwatts of light interacting with mechanical objects. So as I said, we know how to push up to this point 1. That is simply by improving the suspensions. And then to get down to ground state and make this figure of merit parameter go beyond 1, we need a little bit more work. And then comes our optical cavity. So to go beyond what I just told you, we need to really put these torsional pendulums into optical cavities. So this is one of our torsional pendulums that the suspension is from above here. And the pendulum would have a hole in the middle. And this mode that is reflecting from the pendulum, going through the hole and coming back and reflecting, essentially forms a mode inside of the cavity and makes this, what we call the zigzag cavity, purely sensitive to torsional motion. And this forms a way, this is the answer to the question, how do you couple torsional motion to optical cavity to do some cavity optomechanics? And we have a proof of principle demonstration of this. It works. We have a linear scaling of the torsional motion, and it's insensitive quadratically to linear motion, so it's all good. And we're trying to do a high-end experiment. We're trying to do a state-of-the-art experiment using that. The next part of the talk in the next couple of minutes is the other face of the problem, gravity. So we better talk about doing a gravitational experiment if we want to talk about the interface of quantum mechanics and gravity. So we're trying to do that. And the idea is that we first want to answer, can we measure the gravitational interaction of 2 1-milligram pendulums and have that interaction dominant? And the Pathfinder experiment we're doing is the following. We have a gold ball suspended from 2 wires swinging in this direction. It's a swing pendulum. And on the other end, we have a torsion pendulum that is trying to pick up that gravitational, the motion through gravity. One of the major challenges is blocking electrostatic interactions. So we have a shield in between these 2 pendulums. And just to give you an idea of how strong is electrostatics, how strong is gravity, if you take 2 1-milligram spheres, the gravity of 2 1-milligram balls is equivalent to electrostatic interaction of 600 charges. This is in principle doable, but with the shield, the conditions should be significantly relaxed, and right now we're putting 1,000,000 charges on this thing and we're not being able to see any electrostatic interaction. For reference, that's the gold ball that we're trying to detect the gravity of. That's a finger. And Here's how the experiment looks like. In interest of time, I'm just going to skip. So we can swing our gold ball and excite it up to a couple of millimeters oscillation. And from one side, we have the swinging gold ball where we have electrical pads where we can check to see what kind of charges we have on this object. And on the other end, we have this torsion pendulum that's 2 millimeters in scale with the gold balls attached to the end. And if you look from the side, we have the shield in between with about 1 millimeter separation between these two. And it's kind of work in progress. That we don't have any numbers on this yet, but based on what we have, we should be, once we get all the systematics under control, we should be able to resolve the gravitational interaction within a few day time scale averaging. Okay, so I will stop in interest of time. So we tried to make it quantum from one side, make it gravitational from the other, and see how far we can push this to potentially test these ideas of entanglement, gravity-generated entanglement.
So one very, very short question. So can you take the microphone instead?
All right, speak into both.
Okay. This conference requires a lot of manual dexterity. Really nice. I have two questions, if you don't mind. So one is, if you're worried about the electrostatics with the gold, why not use a dielectric? And the second one is,
Why what?
why not use something that's not going to carry a charge, a dielectric, for example?
Sorry, I can't hear.
Maybe just speak
Does it?
without the microphone.
If you're worried about the electrostatics in the gold, why not use like a dielectric or something that won't?
Excellent question. So for this experiment, yes, if we're worried about electrostatics, why not just use some dielectrics and then don't worry about charges? For this experiment, we wanted to deliberately have one of the pendulums conductively suspended so that we can tune the charge to calibrate the effects of electrostatics for the first time. But our torsion pendulum is suspended with a few silica fibers. There is no charge control on this. We plan to eliminate charges using UV illumination, for example. But for this experiment, we wanted one of the pendulums to be electrically tunable just to get a characterization of the role of the electrical interactions. You have a second question?
I was curious about this ADA parameter. You said you had a backup slide, but now I won't be able to get it.
They disconnected my computer.
It's a sort of specific question. So the LIGO number looks quite good, and I was wondering where you're evaluating the force gradient. Like, is it outside of the LIGO mirror or inside of the LIGO mirror?
The force gradient is in those plots. The points are, what if I can bring them to almost touching point? What would be the force gradient of those two objects? Okay. There are two cylindrical objects that are brought together.
Yeah, yeah.
What would be the force gradient between the two?
Okay, so you put the thing outside of the LIGO mirror.
Of course.
Sometimes people miss.
No. This is, okay. We have calculations for 1D, 2D, 3D, how far you can bring close. So it's, okay, thank you.
So let's take one again. And the next speaker is Toccacelo. Thank you very much.
Thank you very much. So this presentation is based on this preprint that is done in collaboration with colleagues Jon Andersen and Jonathan Borras at the Technical University. So I guess I have to. Oh, yeah. Here is. How do I? Is this okay? Yeah. Right, sorry about that. Okay, so as any talk that contains the words quantum and gravity, I have the obligation to include a very cheesy slide, which is I'm sorry if I repeat some things that you already know, but we have this old puzzle, which is gravity quantum? So we have these two theories. One tells us how apples fall from trees, and then we have a framework which describes how cats can be both dead and alive in a superposition. And of course, the big question is, how do we put these together consistently? And Daniel this morning told us that actually we do have a way to do this in a certain regime. This is what we mean by an effective field theory. But eventually, this perturbative approach breaks down in some energy scale. And of course, there are other approaches to the question of quantum gravity, but all of them end up in some sort of problem. So the technical difficulties in themselves are enough to really start to question whether we even need quantization in the first place. And I hope we can maybe debate this later on with a glass of beer or something like that. But ultimately, of course, we want to have an experimental confirmation of this. So the rest of the talk is sort of using some intuition from continuous variable quantum information theory. And so I have to tell you a little bit about teleportation. So you know that essentially the rules of quantum mechanics allow us to establish what we in quantum information theory call a teleportation channel. So imagine you have Alice on one side and Bob on the other. Since we're in Italy, we can also call them Alice and Roberto. And these share some sort of entangled state, which here is denoted by this symbol. And the goal of a teleportation protocol is for Alice to faithfully transfer her state onto Bob's subsystem. So it means to establish this sort of channel here. Now, you may know that this is not possible to do in classical, with sort of classical rules, but we have to qualify that statement because, of course, if Alice knows which state she has to teleport to Bob, she can just pick the phone and tell Bob, prepare this state. So, of course, this is somehow not what we mean when we say that a teleportation is not possible in classical physics. So we have to qualify that statement by saying that what Alice is trying to teleport is a randomly chosen state. And what you can prove in the case of qubit states is that the best a classical strategy can do in this sort of game is essentially, if you look at the fidelity of the resulting state, is this famous 2/3 bound. And essentially, this means that a classical strategy based on local operations and classical communications at best can succeed 2 out of 3 times. Now, there's a version that is appropriate for a continuous variable case. And in that case, for instance, if we consider Alice has some coherent state she wants to teleport, in that case, if you pick randomly the states on Alice's side from this Gaussian distribution, where lambda essentially encodes the spread of the Gaussian distribution, or sorry, the inverse of the spread of the Gaussian distribution, then you can prove this bound. So the way you should understand this is if lambda goes to infinity, this goes to 1, and that means essentially that Alice is always preparing a very definite state with large amplitude. So this is classically possible to teleport. On the other hand, if lambda goes to 0, you get 1/2, which means essentially this is an unphysical case where the Gaussian distribution is completely uniform in the amplitude. And this is the best possible case for the quantum strategy. Anyway, so what does this have to do with gravity? So let's consider this case where we have 2 oscillators that are interacting. Let's suppose that at time t equals 0, Alice prepares the oscillator state in some coherent state alpha, while Bob prepares his state in the vacuum. Now, the interaction from the Newtonian point of view looks like that. And if the interaction strength, which is encoded in this gamma g, is much smaller than the frequency of oscillation of the 2 oscillators, then you can do what we call the rotating wave approximation. And then you get this sort of beam splitter Hamiltonian there. And this is very nice because we know how to solve the beam splitter dynamics. And you can do that in the Heisenberg picture, which gives us these beam splitter transformations. And which means that for certain values of t that we call the swap time, so which is given by pi over 2 gamma g, the state of Alice is essentially, the initial state of Alice is essentially transferred completely to Bob's side. So if we look at the channel established from Alice's input and Bob's output at the swap time, essentially we have a teleportation channel. Well, this is a bit of an abuse of nomenclature, because what we mean by teleportation is really a protocol where two parties share some entanglement and they use this entanglement as a resource to teleport. So maybe this is a bit of a misnomer. Let's just call it communication, and hence the title of the talk. So if we abstract this game a little bit, let's imagine that the interaction, gravitational interaction, is restricted to some sort of box, and we're trying to figure out what the underlying dynamics of that box are. Then essentially this intuition tells us that if we can show that the gravitational interaction faithfully transfers the initial state alpha onto Bob, if we are able somehow to show that experimentally with fidelity greater than the classical threshold that I showed you earlier, the formula with lambda, then essentially we have ruled out that the underlying gravitational interaction, so whatever happens inside of the box, could have been implemented via local operations and classical communication, which in this case actually boils down to a measure and prepare strategy. Okay, so, but in practice, this gamma g is very small because the gravitational interaction is very weak. So we don't really have the full swap, rather we have a partial swap, let's call it that way, where if you go through the beam splitter operations, essentially on Bob's side, if you trace out Alice's subsystem, you get this channel from alpha to this coherent state modulated by the sign of gamma g and t. Okay, so now the question is, how do we put some benchmarks on this dynamics? So how do we test whether this channel actually is what we expect? And the answer to that is we have to modify these fidelity bounds. And now we have a sort of continuous fidelity bound. So just to give you an idea of what this formula means, on this side we have, so let's call the alternative strategy that we're trying to test against. In this case, we're taking LOCC, let's call it epsilon, or sorry, E. We call the output of the strategy E of rho alpha, rho A, and we have to compare it to whatever it is the output of the quantum strategy. Of course, we have some averaging to do, and that's taken care of by this term. And this term here, which is the, essentially ensures that whatever the strategy we are considering is the best possible strategy. And these are, these sort of inequalities were introduced by a work by Ludovico Lamy and collaborators, and they call them LOCC inequalities. Okay, so in our particular case, we have to find the best LOCC strategy for this case where Alice is essentially sending through the gravitational field a message to Bob. And so in practice, you have to assume that your prior distribution is a Gaussian distribution with this sort of spread is the same as I showed you earlier. And the channel is doing this. And what we show is that the bound is then, under these assumptions, is given by this formula here. And just to give you an idea, this is how it compares to the Lamy work that I was mentioning earlier. And these solid lines are these curves given by different values of lambda. Okay, so 2 points. You can see that all the curves, they start from 1. This is what we would expect because at time t equals to 0, there is no dynamics. So whatever the classical strategy is, it should be able to exactly reproduce what the quantum strategy is doing. On the other hand, you see that these curves go down and they have a minimum, and this minimum corresponds to this swap time that I was telling you about earlier. And in this case, that formula above essentially reduces to the Hammerer et al. Bound that I showed you earlier, which is just the teleportation bound. Okay, so with that, just let me give you a very schematic representation of what an experiment would look like to test this. So we have to, Alice has to prepare some coherent state chosen randomly from this prior distribution, and Bob has to prepare the vacuum state. So this is this picture here. Then the systems interact for some time t, at which time we essentially have to check whether the dynamics is what we expect it to be. And in our case, we just need to do measurements on Bob's side. And these measurements correspond to some sort of binary measurement where, so the outcome can be either 1 or 0. 1 is when the dynamics is what you expect, and 0 is when it is not. And of course, you have to repeat this a number of times. So you go and you do this many times, and you build some statistics. And at the end, you compare your essentially the statistics you build from the experiment to the bound that you previously calculated. And if the bound is violated, then you have shown that the interaction could not have been LOCC. Okay, so I will not go, because we have heard a lot about the GIE proposals earlier today. So let me just close with some thoughts. So in this work, what we showed is essentially we determined the bounds on quantum versus classical communication through the use only of coherent states. And this allows us to test whether the gravitational interaction is LOCC or not. Whether LOCC is a good classification for quantum for classical gravity is still not clear. And moreover, this test is done only with measurements on one of the subsystems at the end. And again, it's done without ever measuring entanglement. Now, just to close off with the last point, the Schrödinger-Newton model actually is one of the most well-known semi-classical alternatives to, let's say, quantum dynamics in this case. The Schrödinger-Newton model actually violates both both the LOCC bound in this case and also in the case of Lamy et al. So I think this points to maybe rethinking a little bit what a classical dynamics actually really is. All right, with that, thank you very much.
Thank you very much. So there is one question that already I saw by Cisco. Have you been the first? I saw your hand first. Or maybe, yeah, maybe you start for that. Whatever you think. If you think she was the first. Okay, it's okay. Whatever. Just go.
Which one then?
So that one. So just speak loudly because you want to use that microphone.
No problem.
Okay.
Okay. This is not a. Do you hear me?
No, the one is just one.
Okay. So I don't know if I'm screaming enough. Okay. Now?
Yeah.
So I see that you use only pure states, also Lamy.
Sorry, I can't hear you.
Really? So
It's a bit
I
muffled.
only see pure states. Am
Yeah.
I right?
Yeah.
So also in the case of Lamy, I
Yeah.
guess they didn't do any noise analysis.
Yeah.
But according to you, or because we know that noise is extremely detrimental for any quantum research,
Yeah.
completely kills everything. So how robust do you think that these bounds are if you would add even an infinitesimal amount of mixedness? This is my question.
Yeah, thank you for the question. I didn't have time to go through it in the presentation, but in the paper we do have a noise analysis. And the main challenge is actually to cool the system. And so the quality factors you need for these oscillators is 10 to the 10, something like that. So it's quite challenging, actually. Sorry? The quality factor of the oscillators. And yeah, I mean, I would tell you, in the paper, we have a comparison of the let's say, the expected bound you would get if you have some noise in the system. And we compare those fidelity curves with the bounds themselves. So yeah, it's very challenging.
We actually don't have time for questions, but maybe also we are already asking it.
Okay, a very quick related question. Have you calculated the bound for Fock states?
Have I for what?
Fock states rather than coherent?
Okay, so if you're, for instance, if you say you prepare qubit states, so you restrict to 0 and 1, then we know what the bound is. The trick there, the tricky part there is that the dynamics, so in the coherent state case, the beam splitter essentially keeps the products, product states remain product states. While if you have Fock states, then in intermediate times, if you trace out one of the system, you then have a mixed state, and then it's difficult to calculate these bounds. But yeah, in principle, at the swap time, you have exactly the 2/3 bound that you know from qubit teleportation.
Thank you.
Thanks.
So next speaker, right? So the last speaker is Sajeendran.
Can you use either that microphone or this microphone? Whatever you prefer.
So, which door will you use? This one or?
Oh, that's this one.
Oh, it's this one. Do you want one? Is this USB-C here?
Do you have USB-C?
No, it's HDMI.
You don't have USB-C?
Yeah. Is
HDMI?
Yeah.
Okay. Then let's move the case. Sorry.
Thank you. So I'll be, well, first of all, I'm Achintya. I'm a PhD student from the University of Queensland in Australia. I will be presenting about a project done in collaboration with Zijia Wang, Donghan Yom, Rob Mann, and Josh Fu. And this is on dynamics of quantum fields and quasi-classical spacetimes. It's a project that's in progress. It's not on the archive yet, but hopefully this can generate some discussion. All right, so of course, quantizing gravity remains one of the major challenges in physics. But at the semi-classical level, we can learn a bit about the intersection between quantum and gravity by treating gravity classically and non-gravitational matter fields as quantum. For example, Hawking radiation and the Unruh effect. And this is called quantum field theory in curved spacetime, of course. But this assumes an absolute background structure. So an absolute background metric, so the metric doesn't undergo any sort of quantum evolution, and the back reaction due to matter fields is negligible. So in this talk, I'll be talking about a model that we've come up with for describing the quantum tunneling of spacetimes through a sort of generalized quantum control model. So first of all, I will be talking about quasi-classical states in quantum gravity. I will then go into existing models of spacetime superpositions, phenomenological models. I'll then talk about our model for the spacetime field dynamics. And finally, I'll present very quickly some of our results. So canonical quantum gravity is, of course, one of the earliest approaches to quantizing gravity, and while it is not particularly useful in the sense of testable predictions, as with any other tentative theory of quantum gravity, it's still useful for, in the formal sense, for sort of checking the theory. So, first of all, classical GR is formulated on in 3+1 form. You essentially divide your spacetime into three-dimensional hypersurfaces, which evolve in time along with matter fields defined on them. you choose your canonical variables. The most straightforward choice is the spatial metric defined on these hypersurfaces and their conjugate momentum. And this choice leads to what's called quantum geometry dynamics, a term that was coined by Wheeler in 1958, but in a different context. But anyway, there are multiple different choices that you can make for the canonical variables, and if you choose, for example, the Ashtekar connection and densitized triad, you end up with loop quantum gravity, or at least one formulation of OKG. But I will talk specifically in the context about quasi-classical states and quantum geometric dynamics as they're formulated, because this is at least the most straightforward interpretation to me. Okay, so you quantize in the usual way, propose canonical commutation relations, and from this we can see that there should of course be no such thing as a definite metric eigenstate. So there's no state in the quantum theory that corresponds to a single point in the classical phase space, which is maybe kind of obvious, but this is just contextualizing what I'll talk about later. And so the best we can do are gravitational coherent states. What do I mean by this? Because we can't exactly define an annihilation operator in non-perturbative quantum gravity. It can be done in a linearized case, but not beyond that. So I'm specifically defining them in a kinematical sense as states that saturate the uncertainty relation between some incompatible observables, A and B. Might as well choose these to be the canonical variables, the spatial metric and its conjugate momenta, with equal weights in both. And I think this review by Martin Sod is very nice for understanding how coherent states are defined for general quantum systems. Okay, so in the case of quantum gravity, Lifshitz, there's this nice paper by Lifshitz and collaborators, which basically looks at quasi-classical states in quantum geometry dynamics. And basically what they note is that a quasi-classical state corresponds to a tube in superspace. So this diagram is taken from this Lifshitz paper. And it consists of multiple classical trajectories evolving in time, each iconal trajectory corresponding to a single classical spacetime. And so these quasi-classical states have some overlap with each other in phase space, and they have some probability of tunneling into each other. And this is what motivates quasi-classical states in our model. So now I'll talk about space-time superpositions, which our model is built off of one of these phenomenological space-time superpositions models. Of course, we don't have a complete theory of quantum gravity, but in combining quantum mechanics with GR, I think it's reasonable to expect that superpositions of quasi-classical geometries should be physical states. Heuristically, you can argue this on the basis of combining the superposition principle along with the description of gravitation in GR as curved spacetime. But also, in a formal sense, we can appeal to the Wheeler-DeWitt equation, which says that the Hamiltonian annihilates physical states, and so any superposition should also be annihilated. There are two phenomenological approaches to describing space-time superpositions in the literature. One is through quantum reference frames, QRFs. We had a few talks on that. And the second is through quantum field theory in curved spacetime or controlled under-DeWitt dissector model approaches, such as in this paper by Josh Fug and collaborators. So this quantum controlled under-DeWitt model, it's fairly similar to the original, except you couple to an extra space-time system. So you have a detector that probes the field. You have the field itself, and then you have these MD control operators. So these MDs correspond essentially to mass eigenstates of the black hole, or at least this was the interpretation in the original paper, or metric eigenstates, you could say. And operationally, you could think of these as the states of an ancillary system that's entangled with space-time. Okay, and so I would like to note that both approaches assume that the quantum states associated with quasi-classical spacetimes are orthogonal. So this is also true in QRFs, but in particular in this controlled detector model, you assume that these MA and MBs are eigenstates of some tentative metric operator, some tentative full metric operator. And so if they have distinct, they correspond to distinct masses of a black hole, they should be orthogonal. But really, arguing from canonical quantum gravity and also other approaches to quantum gravity, quasi-classical states should not be defined in this way. And so we should have some small overlap between quasi-classical states. Of course, this is going to be very, very small and almost certainly not experimentally detectable. But it's at least interesting to ask the question of what happens if we include this into the model. And so this allows for some probability of distinct quasi-classical spacetimes to tunnel into each other, and it removed this sort of interpretation as the classical of spacetime as just a classical background structure. And so I'll be talking about our model now. It's sort of based on this controlled detector model. So suppose we restrict the spacetime degrees of freedom to n+1 quasi-classical states, although in principle it can be extended to infinitely many states, but we've specifically been considering this finite case. So we posit that the spacetime field interaction Hamiltonian is of this form, where you have the first term being a free spacetime evolution term, and this alone does drive dynamics in the spacetime because of the non-orthogonality. And the second term is an interaction term between the spacetime and the field. Notice that we've removed the detector completely from this description because we want to understand specifically the dynamics, explicitly the dynamics of the quantum field. Thank you. The HNs here are the free field Hamiltonians in the classical spacetime. And you could say that the classical spacetime closest to the state corresponding to the metric Gn. En it can be interpreted as the ADM energy of the spacetime. For example, in the black hole case, the masses of the black holes. Now, of course, I'm not claiming that we have constructed the Hilbert space for quantum gravity. This is a much, much more difficult problem. But we can assume some Gaussian inner product relation between these quasi-classical coherent states. And we restrict to Schwarzschild black holes of different masses. We can define time evolution by a clock at spatial infinity, so referring to the conditional probability interpretation on page Wooders. And the space-time field state is evolved with respect to this space-time field Hamiltonian H. All right, so I will quickly just get into some of the results here. First of all, consider a qubit coupled to the spacetime rather than a field. You have the spacetime in one of the quasi-classical states and the qubit in a superposition state. And we find that if we restrict to two black hole masses, the qubit will decohere in decoherence time given by this. So this doesn't happen when there's no overlap between the states, but it does happen in some fairly large, practically finite time, if there is some overlap. Secondly, we have entanglement generation between non-interacting bosonic modes. And this essentially comes from the probability for the spacetime to tunnel from one global state into another. And it doesn't happen when the overlap between the quasi-classical states is 0. And this, in principle, would be, at least I think it would be a quantum effect, quantum gravitational effect, because I don't know how else you'd describe a space-time tunneling into another one. Finally, we have corrections to Hawking radiation if we have like a probability of a black hole of some finite mass, correction that gets smaller and smaller with the mass of the black hole, and so you recover a thermal spectrum for macroscopic black holes, which I think is very important given the deep analogy between the laws of classical black hole mechanics and thermodynamics. So those are the conclusions, and I will just leave them there. Thank you.
So we have time for one question. You have to move to the front a bit because the microphone is not working.
Yeah, I'm here. Oh. This doesn't work. On the foot. Yeah, thanks. Can you hear me okay? How's that?
Yeah.
Great. Okay, yeah, thanks. Super interesting. Thank you. So, if I understand correctly, when you follow the canonical quantum gravity perspective forward, you come to a point where the gauge freedom means that you kind of can't really understand the gravitational degrees of the space-time degrees of freedom the gauge symmetry, excuse me, means that you can't understand the gravitational degrees of freedom as a separate degree of freedom from the matter ones. How does that relate to trying to associate a Hilbert space with the gravitational degrees of freedom? And in particular, do you think that one might actually be able to express that mathematically as an effective space with non-orthogonal states? Does that make any sense? Maybe not.
I'm not entirely sure, but maybe we can talk during the break or something.
Yeah, sorry, maybe a little too. Yeah, thanks.
Okay, so let's thank the speaker again. So we start again at 4:45. And the first speaker of the next session, let's look at Gallock-Yoshimura, this is the first year. Thank you. All right.
So thank you for the introduction. I'm Ken Gallock-Yoshimura from University of Tokyo in Japan. And today I'm going to talk about my recent paper on acceleration-induced radiation. So what is acceleration-induced radiation? So in classical theory, it is known that an accelerating charge or structureless scalar source emits radiation, and this is known as LeMaitre radiation. And here I have a picture of this structureless scalar source. And by structureless, I mean that there is no internal degrees of freedom. And so if this thing accelerates, then it radiates. And mathematically, if you have a scalar field theory, then the source is J in the right-hand side here. And the emission rate of this radiation is known as this LeMaitre formula, which is given by this form, where lambda is the coupling constant and A is the acceleration. On the other hand, in quantum theory, instead you have a quantum particle with internal degrees of freedom, and because this internal degrees of freedom interacts with the field, it radiates, and this radiation is a quantum radiation. And at least in 3+1 dimensional Minkowski space-time, this radiation occurs. And in the past, people have investigated the radiation from harmonic oscillators and qubits. But no one has investigated for qubits, which is D-level quantum system. So this is our main focus in this paper. Now, what's the central question or problem in our paper? So in the previous paper done by these guys, it was found that gapless qubit radiates at the same rate as structureless classical source, and therefore they concluded that gapless qubits are equal to classical sources. Now here, gapless means your qubit has 0 energy gap, and the rate is basically the particle produced per unit time. Okay? So they found that this gapless qubit emits radiation as if it is structureless classical sources. Now, our question is this really true? Or more generally, what about qubits, the D-level quantum systems? Is this result a very special case for D equals 2, the qubit? So to investigate, we computed the emission rate for acceleration-induced radiation from gapless qubits. And here, why gapless? Well, gapless qubits enable us to analyze non-perturbativity, meaning we don't have to rely on Dyson series expansion, so that's a good thing. And what we found is that indeed gapless qubits are not equal to classical sources because the radiation emanating from qubits are, well, fundamentally quantum, which is very different from classical radiation. Okay, so I'd like to show you a very small calculation or the setup. So we model our qubits as a spin J quantum system. So the D equals to 2J plus 1. And interaction Hamiltonian is given by this guy, where chi is the switching function, and J plus minus are the raising and lowering operators, and omega here is the energy gap. Now, since we are interested in gapless qubits, we set omega equals 0, which leads to this Jx cross phi kind of interaction Hamiltonian. And this Hamiltonian describes this gapless qubits coupled to quantum scalar field. Now, by using this interaction Hamiltonian, my time evolution operator can be expressed in terms of these two exponentials, which are given by these guys. Here, this lambda is something called space-time smearing function, and GR is the retarded Green's function. Okay? And the point is, we didn't use Dyson series expansion because the gapless qubits enables us to do this. And you might wonder, where's this information about acceleration trajectory? Well, it is encoded in the field operator. In particular, if I perform mode decomposition, it can be decomposed into something called Unruh modes, which is basically a sum of Lindner modes, and these Lindner modes contains the information of the acceleration trajectory. Okay. So by using this non-perturbative analysis, we can compute the final state of the system, and therefore we can compute the emission rate of the radiation. So our main result is that the statement saying that gapless qubits are not equivalent to classical sources. So to show this, I have two main points here. One is the acceleration-induced radiation is correlated with the gapless qubit. And to show this, suppose I have an initial state where 0m is the Minkowski vacuum, and psi 0 is the initial state of the qubit, where it is expressed in terms of Jx basis. Then I can apply this time evolution operator, which leads to this final state, where this d is the displacement operator of the field. So meaning the emanating radiation is the multimode coherent state. And if I express this in terms of this simplified expression, I get this kind of form, which, so this alpha is the coherent state of the field. And as you can see, alpha depends on mx. Mx is the internal degrees of freedom of the qubit, and therefore it is correlated with the qubit, which cannot be seen in classical theory. Okay? The second point is that general expression for the emission rate depends on the internal structure of the qubit. So if the initial qubit state is expressed in terms of this guy, which is basically very general expression for a qubit, so qubit's density matrix, then the emission rate can be computed, and it looks like this, where the first factor is the Larmor factor, which can be seen in the classical theory, but it is multiplied with this thing, which is internal structure of the qubit. So the emission rate depends on qubit's initial internal degrees of freedom, and therefore gapless qubits are not equivalent to classical sources. So pictorially, you can imagine a kind of a sphere where x-axis and z-axis represents angular momentum operator like Jx and Jz. And because I have gapless qubit, my z component is squashed, but you still have this x component. So if I have a qubit system, so 3 eigenstates, then each state couples to the radiation, and this represents what I wrote here. So, in summary, we asked the question, what's the difference between the acceleration-induced radiation emitted by structureless classical source and gapless qubit? In classical theory, which is a Raman radiation, the radiation is uncorrelated with classical source, and the emission rate is described by this Raman's formula. However, in our gapless qubit case, the radiation and the internal degrees of freedom are correlated, and also the emission rate is expressed not only in terms of Raman factor, but also qubit's internal degrees of freedom, and therefore they are very different things. Okay, so this is end of the talk. Thank you for listening.
Thank you very much. So, are there any questions? Right in front of you.
Hi. Thanks for the talk. I was just wondering, what switching function did you use for this? Was it on for infinity time beforehand, or what?
Yeah, so the question is, what's the switching function? And we use the constant switching in order to derive the rate of the emission. So basically, although you are switching constantly, you kind of have like a response rate, right? Like when you compute response rate, you assume like switch on at minus infinity and switch off at some point, but you know, like that kind of stuff. So it's a constant switching. Yeah.
Any other question? Yeah.
Yeah, thanks for the talk. I was wondering, so for the qubit case, do you also see the radiation for just 2 level?
For qubit case, yes. So for qubit case, we see radiation. So for example, mx is 1/2, so it reduces to a kind of proportional to Raman's formula. So in the previous paper, they use like qubits, and the reason they have like Raman's formula for their emission rate is because it's just coincidence.
I see.
Yeah.
Okay. Thanks.
So, one more question. There was another question.
Okay, nice talk. I just wanted to point out that even for qubits or harmonic oscillators, the quantum irradiation also.
Sorry.
Oh, the quantum radiation of harmonic oscillator detector or qubits are also depends on their parameters of internal degree of freedom, and also the initial conditions of the internal degree of freedom.
So you're saying qubits and harmonic oscillators depends on the initial state?
Right, and the parameter of the initial state and internal degree of freedom.
Yeah, so the internal degrees of freedom is the initial state of the qubit. That's it?
No, I mean, for example, a parameter of internal degree of freedom, natural frequency of the harmonic oscillator is a parameter of the internal degree of freedom, and the initial width of the Gaussian state is the initial state of the internal degree of freedom. Yeah. So I mean, your table is not only for gapeless qubits. It can be. I mean, quantum parts. It can be for qubits and for harmonic oscillators.
Okay, maybe we can talk later.
Sure, sure, sure.
Okay?
Yes. If you have HDMI. No.
C'è qui.
This is not HDMI. This is USB-C.
Sì, qua. Come preferisci. Okay, you can see the cars.
Perfect. And you can use the projector, the pointer if you like. Yes, thank you. And the microphone. Please attach that microphone. Maybe to your. You have to attach it to your.
Ah, okay. No, se no uso questo, Goffredo, che qua. Questo è sorry. But it disappeared.
It disappeared.
So
Is it on here as well? Or?
Yeah. Ah, okay, now it works. But no, it's better I use this, sorry.
Yeah, but okay.
Goffredo, meglio che uso questo perché.
Okay, come on.
This one or this?
No, this one.
Ah, this one, ok. Scusa.
C'è appena giù
Control L. Yeah.
Vabbè, puoi pure lasciarlo così,
Can we do
So-
it in a way that is not going outside of...
Thank the organizers for the opportunity to give this talk. I would I will give a short introduction and then I will present a couple of recent results in the context of relativistic quantum spacetime and observers in relativistic quantum spacetime. Okay, thank you. Essentially, well, I will take advantage of the nice introduction by Julia of this morning. Just a short motivation for what I mean by quantum spacetime is a spacetime characterized by a fundamental length scale, which is considered to be the Planck length that comes from the attempt of unifying general relativity with quantum mechanics in theories of quantum gravity. So one of the fundamental problems of quantum gravity is the problem of localization of a point in spacetime. And several hints point towards the possibility that there exists a fundamental length under which it is not possible to make, to perform any measurements, so to describe points. So this is somehow the assumption generic under which we could characterize what we mean by quantum spacetime. And if we think of, and this is what I mean in these slides at least, if we try to model it, then one question arises is what is the fate for relativistic symmetries in a spacetime characterized by this fundamental length scale? So if we make an analogy with electromagnetism, we know that light traveling in a material medium basically could have a velocity depending on the speed, and on the direction of propagation or on the frequency of light. In general, if we think about the transition from Galilean relativity to special relativity, we know that the existence of an invisible ether, like a medium in which light travels with the speed c, has been ruled out by Michelson-Morley experiment. So one of the questions regarding symmetries of quantum spacetime that arises is quantum gravity empty spacetime acting like a dispersive medium, or in that way, is there some sort of quantum gravity header, so a preferred frame characterizing the propagation of signals? This is interesting also phenomenologically, because if you consider light, ultrarelativistic particles with a wavelength which is high enough, so energy which is high enough, it could somehow be sensitive to this microscopic Planckian scale, okay? And if it propagates in empty spacetime, it could carry the information of the tiny Planckian effect that characterizes spacetime. And this in principle, oh sorry. Ah, it's there. Okay, it doesn't matter. I thought it was only on this screen, but it's okay. So in principle, this is interesting because if we consider particle traveling through very high distances, so cosmological in a sense, so astrophysical particles, then we can. There are actual experiments that are capable to, as Julie has mentioned this morning, to reach the sensitivity to test this kind of modification of the speed of ultrarelativistic particles. So one kind of experiment, which is one of the most studied, is the simultaneous emission of ultrarelativistic particles from a distant cosmological source with different energy. So in some scenarios of quantum spacetime, they travel with a different velocity depending on their energy. So you expect that the most energetic particles arrive, even if it is emitted simultaneously, arrives at a different time with respect to the low energy one. Okay. So now, but now I want to focus on the symmetry of this kind of scenario. So, as I said, there are basically two complementary possibilities, two macro categories that we can identify. One is a scenario where this quantum spacetime breaks Lorentz invariance. So, essentially, quantum gravity in empty spacetime acts like a quantum gravity ether in a similar way as Galilean spatial ether was thought of. Okay, so in this case, for instance, some of the kinematical laws that describe the propagation of particles, like the dispersion relation, that could be modified by theories of quantum spacetime, have a particular form only for a preferred class of observers. Okay, this is the scenario of Lorentz evaluation. The complementary scenario, which is the one that I'm going to talk about in the slides, is the one where quantum spacetime is still relativistic. Okay, what does it mean? That by assumption, some of the kinematical laws are modified at this scale, at the Planck scale, but they have the same form for all inertial observers. Okay. For instance, the dispersion law that describes the energy and momentum of a photon. The price to pay is that in order for this to be a law which is valid for all inertial observers, basically one has to modify the transformation within the coordinates of inertial observers. So these are no longer the standard Lorentz linear transformations, but become nonlinear and depend on momenta, and of course they're modified, and the modification, the deformation is triggered by the Planck scale. This is the scenario that is usually called DSR, in the sense of doubly special relativity or deformed special relativity. And in this scenario, the minimum length characterized quantum spacetime is a relativistic invariant. Okay, it's the same for all inertial observers. Or in the other LIV scenario, this depends on the state of motion with respect to the preferred frame. Okay. One of the striking aspects that come out when one considers the possibility of having a relativistic quantum spacetime,
okay, so a DSR scenario, so this is that what happens is that when one introduces a scale which has the dimension of an energy into the laws that govern the relativistic transformation, okay, what happens is that the notion of locality must be relaxed. From the concept from a relativistic point of view, this is similar to what happens, or analogous to what happens when you deform Galilean relativity in order to obtain special relativity, and you have to relax the notion of simultaneity. Here, what you have to abandon is the notion of absolute locality. Okay, so this was realized we realized it some years ago, and the picture that emerges is that the notion of locality and of measurement and the objective description of space-time makes sense in the coordinates only of observers that are local to the measurement process. So space-time makes sense only locally. Okay. The technical challenge in order to manage this kind of theories or models is that one has to rely on the action of the set of this deformed generator to obtain the description of measurements different inertial observers that are distant from each other, boosted or rotated. Okay, what cannot rely on an absolute notion of space-time for distant events. Sorry, something happened. Someone has removed it. Okay. Okay. So this is somehow the consequence of this is that one gets misleading inferences. So if one considers the description of space-time from a single observer, one have misleading inferences about what happens distant from the origin of his reference frame, and the error grows with the distance. This is again analogous with the misleading inferences that one gets in special relativity about simultaneity, which are triggered by large boosts. Okay. Okay, so now in the second part, so this was the introduction. Now in the second part of the talk, I just, how much time do I have left? Okay, I just mentioned two applications of this strategy of analysis that relies on the description of symmetry generators. One is the description of DSR effect, like in vacuum dispersion, the one that I was mentioning before, in a spacetime which is expanding, so in a FLW spacetime. And the second is the study of time dilation in a DSR scenario. Both of this work, recent work, have been done with a group of Naples and with people that are here, like Domenico Frattolillo, Giulia Gubitosi, and Pietro Pellecchia, and Marco Refuto, and Giovanni Emilio Camellia. So for the first example, basically the idea is that you want to study since you need cosmological distances to study this time delay effect, this vacuum dispersion effect that I was mentioning at the beginning. So what we wanted to achieve is to describe it in a more realistic framework, which is the one of an expanding universe. So we wanted to make a DSR formulation in a Friedmann-Robertson-Walker spacetime. The problem is that since you need the action of all the symmetry generator, Friedmann-Robertson-Walker doesn't have time translation generators. So what we did is to use an approximation of Friedmann-Robertson-Walker solution given by the Sitter spacetime, which can be thought of as an expanding universe where the expansion rate is a constant. And then we study the deformation of the Sitter spacetime, because in the Sitter spacetime you still have at your disposal all the relativistic symmetry generators. So you can deform the algebra of generators and study the DSR framework in that way. So the idea is to divide the FLW spacetime in slices of the Sitter. Then we put observers basically at the border of each slice, okay? And we study the exchange of signals in a deformed Sitter. Each slice is a deformation of the Sitter. a DSR deformation of the sitter. So we study the propagation of signals between observers placed at the different slices, and we take the limit for slices going to 0 and the number of slices going to infinity. And essentially, at the end, we obtain the point of view of the observer, which is at the detector, okay? And we obtain the formula. And in this recent work with Giulia Gubitosi and collaborators, we did consider the most general first-order deformation of the de Sitter algebra of relativistic symmetries, and we were able to obtain, through this slicing procedure, the formula that describes the expected in-vacuum dispersion and time delay that could be used in these phenomenological studies. This depends on the redshift of the source. So in this lower part, Z is the redshift which describes the distance of the source. Yes. The second example that I wanted to give is this recent work that we just published recently about the study of time dilation in a DSR scenario, and this is with Pietro Pellecchia and Giulia Gubitosi, Marco Refuto, and Giovanni Amino Camelia. In this case, we consider a specific case of deformation, which is the one described by the so-called famous K-Poincare deformed symmetry algebra, but we considered it at all orders in the deformation parameters because we wanted to consider finite boost, okay? And we were able to obtain the finite boost transformation of all the phase space variables, the coordinates of particles and the momenta of particles. Here, eta is the parameter of rapidity that triggers the boost. And the result that we got is a relation between the velocity and the rapidity of particles, so a generalization to the former DSR model of the relation between the velocity and the rapidity of the boost. Okay, so usually the velocity is just the hyperbolic tangent of eta. Here, this is the forming function of L. We managed to find that the underlying space-time can still be described by a metric which is covariant under these symmetries. The metric, which is this one, depends on the energy. Here, epsilon is the energy of the particle, so the metric itself becomes energy dependent, and we obtained the time dilation factor, which is the ratio between the time measured in the laboratory and the proper time of the particle, which is a deformation of the special relativistic time delay. One thing to notice is that this is different from the gamma factor that you get from the ratio between the energy and the mass of the particle. Okay, thank you, and this is the lecture. Thank you. Yeah, thank you.
The next speaker would be online, but the person is not online, so we just go for the not one after. Dimitris Moustos.
Pubblicità agli articoli, adesso mi compro.
Giacomo just run away with it.
Sì, vabbè, comunque è fuori da, c'è pure out of topic, secondo me.
Non neanche dovuto ascoltare, which means we have 5 minutes left, but that includes the questions. Okay. So if you want to have questions, then we should end earlier.
Okay, thanks. Can you hear me? I guess.
Then maybe use the other one.
No? Oh, or no?
Yeah.
Yeah, okay, good. Seems to work. Okay, thanks. First of all, thanks to the organizers for giving me the opportunity to present a research work of mine that was done in collaboration with Obinaba at the University of Newcastle. And also I would like to thank the... Now? Okay, thanks. And of course to thank the local organizers for... Yeah,
there's no problem. That's
I
just the
don't
other
know.
one.
Yeah. Now? Okay. For organizing this conference. Okay, so I'll start with some introductory context. Over the past few years, there have been a significant advance in quantum thermodynamics, a field that studies thermodynamic processes and thermodynamic quantities like heat or work in the quantum regime. And along with the breakthroughs in engineering and controlling quantum systems, an idea and a question has arisen if we can design quantum thermal machines, that is thermal machines that has as a working medium quantum systems or just a simple quantum system like the cartoon here where an atom is confined in a piston that can be modeled, for example, with an optical cavity. But the very first theoretical proposal of a quantum thermal machine was given in 1959 by Scoville and Dubois, where they proposed a three-level measure as a prototype for a quantum heat engine. And since then, there have also been many implications in experiments of quantum thermal machines. For example, using just single ions in ion traps, or some implementations in superconducting circuits. And the most of studies, both theoretical and experimental, are focused on quantum auto-thermodynamic cycle, where the working medium is just a qubit or an harmonic oscillator that undergoes 4 consecutive strokes, 2 adiabatic and 2 isochord. And when this condition is satisfied, the thermal machine can operate as a heat engine, producing useful work, and where its efficiency is bounded by the Carnot limit, as in the classical case, but also the machine can work as a refrigerator when this condition is satisfied. And in this case, its performance again is bounded by the classical Carnot limit. And in recent years, there have been also research and interest in the community of how we can translate these thermal machines, quantum thermal machines, in relativistic setups, where in this case anode Derby detectors play the role of the working medium, and the quantum fields, relativistic quantum fields, model the thermal bath. And I just present some works here, and most of these works are focusing also on calculating, evaluating the work output of these heat engines, relativistic quantum auto heat engines. But what I want to present here is a general framework for studying the finite thermodynamics of such relativistic quantum thermal machines, and mostly I will focus on studying their performance. And what I mean with this one, because as I said before, and as we know, quantum thermal machines are bounded by the Carnot limit. But okay, this is a very ideal situation. Achieving the Carnot limit is practically unfeasible because it requires infinite slowing processes to ensure adiabatic evolution, and also requires infinite interaction times with the thermal baths so to have a complete thermalization with the bath. And for this reason, a more practical measure of the performance of the heat engine, in this case, is its efficiency at maximum power. And what this means is that we want to optimize, to maximize the work output of the machine with respect to some parameter of the system, which usually for, let's say, in this case for a qubit, is the omega hot frequency. And a relevant expression for efficiency at maximum power in this case was given by Curzon and Alborn, through this expression. And another measure, a figure of merit of the performance of heat engines, of quantum heat engines, is employing the ecological criterion, which is implemented through the so-called ecological functions, which basically embodies the trade-off between maximizing the power of the heat engine and minimizing the ecological impact, the ecological waste of the machine, which is quantified by the entropy production. And again, optimizing this ecological function with respect to some parameter of the system, we can calculate its efficiency. And relevant measures is for the performance of the refrigerator in this time include coefficient of performance at maximum figure of merit, which is the product of the coefficients of performance of the refrigerator and the cooling power, and its cooling power, which also can be optimized for some parameter of the system. Here a relevant relation was given by Yan Chen, and also employing a relevant ecological criterion in this case. And okay, what we are doing in this work, we are trying to make all this concrete in a model of interacting with a conformally coupled scalar field in a 2+1 BTZ spacetime, which in this case it is known, the Weidmann function, the Weidmann two-point correlation function is known analytically, which simplifies a lot the studying of the dynamics of the detector. And let me focus on this parameter here, which is the zeta parameter, which gives the different boundary conditions that can be imposed in order to have a well-defined quantization scheme. Okay, so this two-point correlation function is known to satisfy the KMS condition. That means that the quantum field basically behaves as a heat bath at this temperature. And this means also that we can use, so we can, by coupling the enanoid David detector through the conformal field in the black hole spacetime, basically it's like coupling it to a thermal bath. We can calculate analytically the dynamics of the detector by employing a master equation to describe the reduced density matrix of the detector, which can be solved analytically, so we can have the full time evolution for our detector. And we can introduce an orthothermal machine, in this case, where during the isochoric processes, the detector interacts with the field that now can serve as a hot or cold bath. And we can now use finite time interactions with the hot bath and finite interactions with the cold bath. And again, since we have the solution, the analytic solution of the reduced density matrix, we can also calculate and have analytic expressions for the work in heat in each of the 4 strokes of the engine, of the machine. And okay, in this case, we can, when the thermal machines operate as a heat engine, we can evaluate its work output and show that the Neumann boundary conditions is the optimal one for finite time operations of the machine. And we can also calculate the efficiency at maximum power and efficiency at maximum ecological functions, which, okay, they, of course, they do not violate the Carnot bound, but it seems that they can surpass the Cruson-Albert efficiency. And also, we can calculate the cooling power for the refrigerator mode of the thermal machine. Here is more clear that the cooling power is optimized for, again, for the non-boundary condition. And again, we can calculate the coefficients of performance at maximum figure of merit and at maximum ecological functions, which again surpasses the relevant Janssen limit. And we can approach the Carnot bound in this case. And okay, what are the motivation of this work beyond by presenting a general framework for studying the performance of relativistic quantum thermal machines is that this setup under the V detectors and can be can be designed in analog experiments, and most importantly, 2+1 BTZ black hole can be modeled in analog setups. For example, we know that some implementations employing quantum fluids have been in the literature, and we would be very interested in seeing possibilities of studying and quantum thermal machine in some analog models, and we are welcome any feedback for this case, and thanks for listening.
Yeah, thank you very much. Are there any questions?
Just speak at the boat.
All right. Thank you for the talk. So I want to ask about the cyclicity condition. So did you impose a cyclicity?
You can impose if you want to close the cycle,
Yeah.
but it's not needed. I mean,
okay,
you can calculate it work. Okay, the first thing if you want to study finite thermodynamics, it's you can study work and heat exchange at any time, okay, and then you can allow the system to thermalize, for example, with a bath, so we can close the cycle and start again.
Yeah, so my concern is like, because you have finite time interaction, it does not necessarily thermalize to something.
It's not exactly thermal, yeah.
Yeah, so
it's
I was wondering like how people do it.
Okay, yeah, you mean using, it's not a thermal equilibrium bath, but basically it's a non-thermal equilibrium bath. You mean that? But this is something very common in quantum thermodynamics and thermal machines. I mean, you cannot have complete thermalization in some experiment, for example, okay, or complete adiabatic evolution. So considering finite time is also more interesting from the perspective of experimental setup. So, but in any case, theoretically, you can allow fully thermalization, fully adiabatic evolution, and close the cycle, and again start the cycle. And, yeah.
Thank you very much.
Another question?
Sorry, this is actually a question to both you and Ken, because I know that both of you have worked on the relativistic heat engine. And it's so when you do the cycle, right, you have to return to the same initial state, otherwise you don't have the full cycle, right? So you have this, usually when you interact with the field, you have the noise that the field adds to your detector, right? This is a general feature that happens whenever you interact with a quantum field. It's like you're in this open environment. So up to some extent, you need to like purify, if I understand correctly, your state to really come back to have the cycle close, right? Of course, this costs work, right? There's also costs work for you to go from your mixed state to your initial state, effectively, right? For you to play with this idea. So, is there any kind of estimate regarding the amount of work that you will need to perform to really close the cycle, including this step of really purifying, quotation marks, the state? It's a question to both of you. If any of you know the answer or something, I don't know.
I don't get the exact question, but yeah. What do you mean? Can you say it again?
Sorry, can you repeat it?
Basically.
Yeah, the question is, is there an estimate for the amount of work that would be required to actually close the cycle, to purify your state, to come back to the initial state?
Well, it's a good question. I have no clue on that. Of course, in this, closely related to this question, if you want to study the energy, what energy is needed to build the cycle also, one should also check and study the energy that is needed to make the interaction. Okay, so yeah, this is a different thing to have in mind. Yeah.
Okay, thank you. Ken, do you want to add something to it? I mean, if it, huh? Okay, yeah. Thank you.
Supposed to be green?
Yeah, that's right. The next speaker is so that's the HDMI. It doesn't. You can just use. But that's HDMI. This is not HDMI. This is
USB-C. Oh.
Exactly. That's perfectly.
Nice.
Yeah, perfect. So next speaker is Philip LeMaitre.
1 second. Oh. What's going on here? What's going on here?
It looks like it has a conflict.
Should I just use
between the two? Maybe just wait.
Okay, that's weird.
Okay, use the HDMI.
Okay.
Only one entrance.
Yeah. Yeah.
Also put there.
Okay.
Ah, okay. Nice. Okay, cool. Okay, I can't really see this. Okay. Oh, need the mic. Okay. Thanks for. Happy to be here. I'm Phil LeMaitre. I'm from the University of Innsbruck, and today I'm going to be talking about work that I did in collaboration with Rick, as you all know, postdoc from my group Marius, and my supervisor Hans Briegel. And it's going to be about a universal quantum computer from relativistic motion. Okay, so the original question that we wanted to answer was, what does quantum computing, what does a full quantum computer look like in the RQI setting? So we have lots of quantum information protocols like in entanglement harvesting and quantum energy teleportation, but we want to think about more general protocols maybe, or have a general platform to implement these protocols on. So what does it look like? We have some answers to this question in these works here. They talk about constructing 1 and 2 qubit gates using relativistic motion. And so what we would like to do, or what we did, is to build on these proposals. Build on these proposals and give a complete universal quantum computing architecture in the relativistic setting. So more specifically, we're going to show that you can execute quantum computation using only detector motion and field-mediated entanglement. We're going to show some analytic expressions for the gates, which was, as far as I know, only done perturbatively in the existing literature. We are going to show that the noise from the field can be made negligible in some regime. We'll show some analytic bounds for that. And we'll show that it's actually a universal quantum computer. Okay, but first, so it's in the paradigm of variational quantum computing. And so I'll just give a quick rundown of what that is for people who don't know. So imagine we have this, this unitary here, and we break it down into various layers of unitaries. And in each unitary, you have some entangling, some set of entangling gates, and you have some one-qubit operations, which are parameterized by these parameters theta. So, and here's what the one-qubit rotation operators look like. So what you do is typically you feed in an initial state. It runs through this, you apply this circuit, you make measurements, and you calculate this function here, which you then implement, you put into a loss function, and what you do is you try to minimize this loss function, and this gives you an update for the parameters in the circuit. And then you repeat this as many times as you need to get some, let's say, you want to mimic some unitary operation, or you have some data that you want to fit your unitary to. So you do this a number of times until you've minimized the loss function sufficiently. So that's what variational quantum computers do, and our proposal will look something like this. Okay, so let's start with the local operations. So imagine we have this, let's see, is it working? Okay, well my laser pointer's not working, but I can use this one. Okay, so imagine you have this nice array of black circles here. These are supposed to be UDW detectors. And each of them is following some world line, some trajectory. And so this will be, we have our nice free Hamiltonian, which we parameterize with the rotation angles, and we parameterize with the actual direction that we make the measurements in. So these are our one-qubit operations, the U-para that I showed in the previous slide. And so the trainable parameters that we take are the energy gaps and the proper time difference. So what's different here, as opposed to previous or non-relativistic quantum computing, is that instead of tuning the energy gaps, you can just tune the trajectories in space-time themselves. So this is what we mean by relativistic motion. And you can see this in some of the previous proposals as well. So these are the one-qubit gates that we have in our setup. And now we consider the entangling operators. So we have the classic interaction Hamiltonian for UDW scalar field, massive scalar field setting. And so in the original, we had our free Hamiltonian dynamics. And now you can imagine turning off the dynamics by making the energy gap 0. So we go to the gapless case. And then we essentially turn on this interaction in this regime. So these little blobs are the smeared regions where it interacts with the field. And so what we get, actually, because we are in this special setting, is these analytic expressions for the decoherent channel here. So in the next slide, I'll show you why we can ignore it. We can consider this to be identity, and we can just have these as the entangling gates for our quantum computer. So these this is just the symmetric propagator, and it just depends on the retarded and advanced propagation through the field. So it's just, this is just the field-mediated part. And we have to impose this condition of meaningful entanglement. Because we're working in this regime, you need to build up the entanglement for quite some time. So we have to impose this relation if we want to be able to do any quantum operation. And as I said, yeah, it entangles all of the qubits that interact with the field. So we get a kind of something that entangles everything for free in one shot. But as we'll see, this maybe is not so desirable. So in the next slide, I'll show you how we can get universality. Or sorry, not the next slide, but in 2 slides. Okay, so this is this is what the entangling looks like. And now I'll show you why the noise is actually negligible from the local interactions with the field. So what we did is we have this channel fidelity. So this is the full decoherent channel, and this is just the unitary part of the channel. And so we derived this lower bound. So if you just take this to be a pure state, this will just be 1. And we have this as the lower bound. So it doesn't look, it looks like it's usually small, but if you consider, so we have the meaningful entanglement here, and we have this condition to make this much smaller than 1. So this will guarantee that the lower bound is essentially 1, which means that they're basically indistinguishable. And so we have this is the condition that we work with in our setting. And this is also true for general spacetime. So we didn't assume any specific form for the spacetime. And so if you want to take this to time scales, if you want to show the time scale, then you actually get this condition that the length between the detectors has to be much smaller than the typical time scale that the interaction takes place over. So for example, if you just had Gaussian smearing in Minkowski, this is, why is this happening? Okay, this W term is what it would look like up here. And if you put in some numbers, you basically find that fidelity for one layer is 99.998%. And even if you wanted to have 100 layers, you still have a fidelity of 99.8, which for 100 qubits is pretty damn good, I would say. So you can, within the NISQ era at least, you can take this, you can use this model without any problems about worrying about the decoherent noise from the channel, from the field, sorry. Okay, so then putting that all together, you have this picture looks a little bit complicated, but essentially down here we have our rotation operators that we apply at the beginning when we're just doing the free evolution. And then we get into this, what's going on here? Let me see this, okay. And then we get into this regime where we essentially turn that off and we activate the interaction with the field. And we represent it here with this, channel. And so 1, apply those. 2, couple everything with the entangling unitary. And then you can do this as many times as you want in layers. And this is, then you measure your observable, you calculate this function here, and then you, as I showed you in the variational quantum computing setup, you just do this as many times as you need to. Okay, so I haven't showed you yet how it's universal. We have our 1 qubit gates. We've got something that entangles all the qubits together. But before we did this, it wasn't actually known that this all-to-all connection is universal, or at least we couldn't find anything on this. So what we did is we consider sandwiching these poly X operators on one of the qubits, and doing this in a step. So doing this for all n qubits. And what you find eventually in a linear number of steps is that you can get something which only acts on 2 arbitrary qubits. So you can do this with a sufficient number of layers, and this will give you a 2-qubit gate that is arbitrarily, sorry, this will give you an entangling gate that acts on 2 arbitrary qubits. And so because you can construct this, and you have your single qubit rotation operators, this is enough. This is known to be enough for universal quantum computation. So then what we did to actually show this scheme in practice is to emulate the quantum Fourier transform. So we used 6 qubits, we used 50 layers, we picked this timescale here, this coupling strength, and this spatial smearing. We choose this lattice for the Lij, and we take the monopole operators for the entangling gates to be sigma z, the poly z. And we can get the loss to go down to finally to 0.004, which is extremely good. In terms of the fidelity, so this is the fidelity for an arbitrary ensemble of states. This is going to about 99.6 fidelity. So essentially, it's doing what the quantum Fourier transform is doing to within an experimental, what's experimentally accessible. So yeah, and so that's the scheme. Thanks for listening, and I'd be happy to take any questions.
My question is super quick. Can I just, sorry. Sorry.
You're on the slides.
Was this paper published?
Yes, sorry, oh, yeah, I should have mentioned. This is the link to the paper. I also had it in the first slide, but if you want to check out the paper, please scan the QR code. This was recently published, I think, in, was it March or April? So, what? It was published in Physical Review Letters. So, yeah, it's, we'd be happy if you were to check it out, and if you feel like using it, that would be great.
So I was wondering, you said that using sufficient of the sandwiching of entanglement, you can get any arbitrary 2-qubit entangling gate. Kind of, what is the order? Is it like linear? Like if you have n qubits, then you need to apply n sandwiching operators, or is it better than that or worse than that?
Yeah, no, it's linear. The complexity is linear. So if you had n qubits, you would need to do this operation n times. So yeah, it's like it would be x1 gate x1, and then the entangling gate. And if you want to check out the supplementary material in our paper, you'll see exactly that this does actually converge to something like that. So
cool. Thank you.
All right. So we go for the next speaker.
Yours is on the computer?
Yeah.
There's more one?
Step behind, down there, somewhere.
Ah. Where is it?
I don't know. Ah.
Good. Okay.
Excellent.
So you can use this as a pointer if you like. And after 10 minutes, I show you 5, which includes your questions. Okay.
Okay, well, good afternoon, everybody. Welcome to the last talk of the session. I'm Nicholas Funai. I'm from RMIT University, and thank you very much for offering me this chance to talk about this. So I will be talking about something which is very similar to a lot of things I've seen so far this conference, but obviously, as with all things, slightly different enough to make our own talk. So it's non-perturbative modeling of quadratically coupled detectors in quantum field theories. Oh yeah? I'm sorry. Okay, that's better? Up higher. All right. So this is about my work on non-perturbative modeling of quadratically coupled detectors, and if you want to see more details, you can look at the publication here. All right, so I'm going to start by saying that, emphasizing the importance of phase in quantum theory, and I'm going to say that we all know very well what happens when you lose phase, when you have double slit experiment going on, and we also, so we can go through a very, very simple example of what happens when we have a quantum superposition, and we don't know very well, what role each of the I5 plays in this superposition. So this term here, e to the I5, plays an important role, because when we go to establish what expectation values are of these states, they turn up in sort of cross terms here. And I emphasize that because when it comes to quadratically coupled detectors, something which has been missing in the literature is a way to evaluate, under certain situations, what this phase term looks like. So this talk will be focusing on evaluating what this phase looks like, basically when it comes to superpositions of quadratic Gaussian states. Okay, so when we so I'll be using Unidui detectors, and we often make use of first quantized linearly coupled detectors, and by that I mean that we have a monopole moment, we have a smear detector, and to make this quadratic, I'm not going to make them gapless, I'm going to just use a delta coupling term, so that instead of using the second order perturbation theory, I can just go straight ahead and evaluate things non-perturbatively. And if you, in quantum information language, that means that what this operation will end up looking like is a controlled displacement operator on the field controlled by the x value of the qubit in question. And basically, when you do that and then you go about and try and measure your measure your qubit, for example, if I do a post-selected measurement of what the unitary operator looks like, it'll end up looking like a cat state when applied to the vacuum. And if I do this with quadratic detectors, I will get something very similar, and I'm trying to join the dots here with analogies as well. So the primary motivation for what I'm doing was when I first looked at quantum energy teleportation, and just as a very brief overview of what this looks like, what this protocol is about is, imagine I have Alice interacting with the field at a particular point in space and time, and then over time, the field is allowed to evolve so that an energy packet arrives at Bob, as well as the measurement information associated with Alice's measurement. And then Bob receives the information and then uses information to extract energy, and in certain situations can create a region of negative energy density, or do whatever he likes with it. And this involves two control operations. So a non-perturbative operation interaction here, which is a controlled x with a displacement, and here is a controlled z with a displacement. Okay. Now, when it comes to quadratic coupling, the motivation initially for this was that at some point in time, somebody wanted to do a little comparison between harvesting with bosons and fermions, and they decided that the fairest thing to do would be compare quadratic and quadratic. And so what we'll be looking at is a quadratic detector, which is, has a similar monopole form, but then the quadratic form is slightly different in that we have phi squared. I will be using something slightly different to what others have used, and that is that I will allow these phi operators to act on different points of space. So you can interpret that, if you like, as some sort of UV cutoff, which is allowing these quadratic terms to be slightly smeared amongst themselves. Note that the normal ordering here is necessary to avoid divergences that arise if you don't have that. Okay, so if we repeat the process that we do for non-perturbative detectors and use a Dirac delta function as a switching function, the unitary evolution operator ends up looking like a controlled operation with this S operator, which is a quadratic displacement operator. Now, imagine I would like to do the exact same thing I did with the linear detectors, except with the quadratic detectors. So basically, the same diagram holds, and I use an S instead of a D, and my hope is to do this. I haven't been able to do that yet, but my hope is to see what happens if you do that. Okay. Now, if we look at what the state looks like post-interaction, it will involve a controlled X with Alice's interaction, some free field evolution, and then Bob's interaction, which is another controlled operation. And if we try to compute, for example, any observable associated with this state, basically I bring your attention again to the fact that we will have phase terms arising here. So if we, for example, want to evaluate a specific operator for this state, one of the cross terms in question will involve something that looks like this. It's quite a scary looking expression, but when you take advantage of the conjugation relations that squeezing operators or quadratic operators have, as well as linear displacement operators have, what it boils down to is evaluating this. What is the vacuum expectation value of the quadratic displacement operator? I asked this question many years ago. No one was able to tell me, so I had to work it out myself. Okay, so let's look at representations of this S operator. So the S hat operator is a unitary operator. That is to say, it's the exponential of some Hermitian operator, I times the Hermitian operator. And so I can write it in this way. Its main form isn't that important, but the point is that it's an exponential which involves linear combinations of A's and A daggers and quadratic combinations of those. And as a result, what you can do is you can show that this S operator acting in the vacuum happens to be in the kernel of this linear operation here, this combination of A's and A daggers. And you can just derive that by using, again, the conjugation properties of quadratic displacement operators. But fortunately, what we can also do is we just grab a Fock expansion of this very equation and just say that this state here, this exponential of A dagger, and linear combinations of those acting on the vacuum also is in the kernel. And you can also show, if you want, that this is a one-dimensional space, so these two states are the same up to a complex number, factor. So we have this relation here. We have that the unitary representation of a quadratic state can be given in the Fock representation. We can evaluate what the normalization is because it should be normalized to 1. That's easy, but then we need to know what this phase is. And I, again, emphasize the fact that without this phase, we would basically not know this, and so when evaluating expectation values, we'd end up with classical mixtures instead of genuinely coherent superpositions. Okay, so to evaluate this, you can do what turns out to be quite a simple trick, and that is to effectively get the tangent vector of this particular state. So take a derivative with respect to the lambda, the coupling constant, on the operator in both representations, and then compare them. And so it's very difficult from this angle. All right, so in the unitary representation, the Hamiltonian term basically just drops down, and in the Fock representation, you have to bring down all the derivative of all the junk inside the exponential, and then we can take another inner product with itself and just start saying that, well, we can see that this term will be 0 because H is normal ordered, and it commutes with the exponentials that it generates, and then we just have to work out what this particular expression here is. Unfortunately, we can just stick in, because unfortunately, this expression here is anti-normal ordered, but what we can do is we can just put an identity operator there, write it out as a coherent states, resolution of identity in terms of coherent states, and then just evaluate the resulting Gaussian integral. And what we end up having is that A, so e to the A times the Fock expansion. The A is given by this rather simple expression, which is the trace of a matrix F. This matrix F is a function of the smearing of your detector initially, and a less friendly expression, which is the trace of the matrix logarithm of this matrix F. So thank you. What was previously what previously some people would have tackled by trying to expand this unitary operator and just start comparing terms has now been reduced to a simple question of evaluating traces of matrices and logarithms of matrices. All right, so we can go through a simple example, and this simple example in my case is to say that the smearing function f is a Gaussian. And the great thing about this Gaussian is that you can actually separate it into f of x times f of y. And that actually means that when you compute everything, the F matrix that we are curious for, the cursive F matrix, is rank 1. So it's very, very easy to just evaluate its logarithm and then take its trace. So we have that right here. And that means that we can now start playing with it. And the simplest example I can come up with is the Fermi problem, or the simple 2-qubit communication problem, which basically just says if Alice interacts with the field at one point, and then Bob interacts with it at some later point, depending on what position Bob's at, how much information can Bob extract about Alice's presence. It's basically very, very simple. It should be that Bob should be unaware of Alice's presence if they're space-like separated, should see it if they're light-like separated, and if it's a massless field, he shouldn't really know if it's time-like separated. And this is what you get. Very much what you expect, that when Alice and Bob are time-like separated, which is in this particular region here, you get no communication. The fact that it's non-zero is just numerical artifacts. This is the signal that shows you when Alice and Bob are light-like separated, and then it goes back to 0 again. And if you actually look at the reduced density matrix of Bob after all these interactions have taken place, you can sort of see where the problem of the phases of these operators comes in, because we have SA dagger, SA, those come in conjugate pairs, so that's easy, but you're left with an SB by itself and the vacuum expectation of that. So you have to evaluate this with its phase, because then you have to add it to another term right there. Okay. And then, just for fun, we can also have a look at what is the energy distribution of a field after interaction. We know what it is if we do a squeezing operation or a quadratic operation on the field, and it looks sort of like this. But if we take a linear combination of squeeze states or quadratic states, it changes slightly. You can't really garner any physical intuition from this because it's just a toy example, but the fact is that it's possible to do it now. And basically, I'm hoping this will open the door for anybody who wants to use quadratic detectors in the future. Okay. All right, so on the whole, we've answered this, what was a simple question with a complicated answer, which is what is A, the phase of the unitary representation when you write it in the Fock representation. This framework is necessary for coherent descriptions of superpositions of Gaussian states. And we just also presented 2 basic RQI examples for the coherent modeling of quadratic states. So this will allow us to model quadratic QET, for example. When I get around to it, I'll be happy to do that. It's also, for example, extends the work of previous authors, for example, who do a sequence of delta pulses with linear detectors. Now you can do it with quadratic detectors if you don't mind going through the mind storm of mathematics and arithmetic. In theory, we can now start asking this question about comparing fermions and bosons in non-perturbative areas. And it also, this extends beyond RQI. So for example, we can now look at other near Gaussian systems. So for example, either in quantum optics or in this particular case, relevant here, which is some people are trying to do harvesting with superconducting circuits. So imagine if we look at other superconducting circuits with quantized mass terms or anything quantized which is quadratic. All right, as an aside, I'm currently looking for my next position, so I welcome any advice on the matter. Thank you.
So there's time for one short question.
So this coupling you're using for the quadratic thing with this f of x and y, it's like, it is a non-local coupling, right? In the sense that, like, if you were to write a Hamiltonian density for your interaction, this Hamiltonian density will depend on an integral in space, or space-time even, right? So are there any consequences for causality or something like this by considering this kind of coupling, or is it the same as if you were just considering a smear detector, like a standard UDW?
Okay, so I have not considered what would happen if you try to accelerate a detector of this sense, because that's when you'd want a covariant representation of this. But the way I see it is, well, I chose it because it's mathematically easier, but it does include the examples of when f of x, y is just f of x is equal to y, sorry. But it also covers the area when if you have some sort of band limit on your field and a minimum length scale associated with that, in which case something like that would likely show up anyway.
Mm-hmm.
So I'm going to dodge your question because I don't really know. I would expect that it doesn't play well with covariance in the way you want. But there are other applications for its use. That's basically why I used it.
Thank you.
Okay, great. So let's thank Nicholas again.
Okay. Yeah, just asking whether we would have a Zoom session. Whether we would have a Zoom session, but no, right? There's no Zoom talk.
So we are going to have the workshop meeting here in that room in 10 minutes.
Let me, yeah, just